Every second, the universe stretches farther, holding secrets about how everything began and the mysteries of existence. Our search for understanding takes us from the birth of galaxies and the mysteries of black holes to the possibility of life beyond Earth. Each discovery adds to our cosmic story, showing us what we know and the unknowns still waiting to be explored. The beginning of the universe is a fascinating subject that has captured the curiosity of scientists and thinkers for centuries. The most widely accepted theory for the origin of the universe is the Big Bang theory. According to this idea, around 13.8 billion years ago, the universe began as an infinitely small point, a singularity which then rapidly expanded. This expansion was not an explosion in space, but rather an expansion of space itself. In those first moments, the temperature and density of the universe were extraordinarily high, creating a chaotic environment filled with energy. As the universe expanded, it cooled, allowing subatomic particles to form. These particles eventually combined to create simple atoms like hydrogen and helium. A few 100,000 years later, these gases began to clump together under the force of gravity, eventually leading to the formation of stars and galaxies. This process of coalescence and formation laid the foundation for the rich structure of the universe we see today, with its stars, planets, and galaxies. Other theories have emerged alongside the Big Bang to address questions and phenomena that it does not fully explain. One such theory is the concept of cosmic inflation, proposing that just after the Big Bang, the universe underwent an incredibly rapid expansion, stretching exponentially over a very short period. This inflationary model addresses why the universe appears so homogeneous and isotropic on large scales, despite its complex and clumpy structure on smaller scales. Additionally, some cosmologists are exploring alternatives like the cyclic model, which suggests that the universe undergoes endless cycles of expansion and contraction, or models that involve multiverses, where our universe is just one of many existing simultaneously. Each of these theories contributes to a richer understanding of cosmic origins and invites us to continue exploring the mysteries of our existence within this vast, enigmatic universe. The Big Bang theory is the leading explanation for the origin of our universe, proposing that it began as an infinitely dense point, often referred to as a singularity, around 13.8 billion years ago. This event marked a dramatic expansion, resulting in the universe as we know it today. It wasn't an explosion in the traditional sense, but rather a rapid stretching of space itself, giving rise to all matter and energy. One of the most compelling pieces of evidence for the Big Bang theory is the observation of cosmic microwave background radiation. This faint glow fills the universe and is a remnant of the hot, dense state that existed shortly after the initial expansion. Detected in the mid-20th century, this radiation provides a snapshot of the universe when it was just about 300,000 years old. Its uniformity and spectrum match exactly what scientists would expect from a universe that started hot and gradually cooled over time. Another significant supporting detail is the abundance of light elements, such as hydrogen and helium, in the universe. According to the theory, during the first few minutes after the Big Bang, conditions were just right for nuclear fusion, leading to the formation of these fundamental building blocks. Observations reveal that about 75% of our universe is hydrogen, while roughly 25% is helium, which aligns perfectly with predictions made by the Big Bang theory. Moreover, the expansion of the universe itself offers further evidence. Astronomers like Edwin Hubble observed that distant galaxies are moving away from us, with more distant ones traveling faster. This discovery aligns with the concept of an expanding universe, a fundamental aspect of the Big Bang theory. All these pieces together paint a coherent picture of a universe that has evolved over billions of years from a hot, dense beginning to the vast cosmos we observe today. Scientists measure the age of the universe using several key methods that intertwine observations and theories. One of the most significant approaches is the study of the cosmic microwave background radiation, often shortened to CMB. This is the afterglow of the Big Bang, a faint remnant that fills the universe. By analyzing the temperature fluctuations in the CMB, researchers can infer the conditions of the early universe. These measurements are crucial because they help us understand the rate of expansion of the universe, known as the Hubble constant, which in turn allows scientists to estimate its age. Another primary method involves observing distant celestial objects. Astronomers look at the oldest stars in our galaxy, particularly those in globular clusters. By determining the chemical composition of these stars and measuring their luminosity and temperature, scientists can estimate how long these stars have been shining, providing a lower limit on the age of the universe. Some of the oldest known stars are around 13 billion years old, reinforcing the notion that the universe must be at least that old. Moreover, the study of the expansion of space itself plays a crucial role. Edwin Hubble's discovery that galaxies are moving away from us indicates that the universe has been expanding since the Big Bang. By applying the laws of physics and measuring the distances and velocities of these galaxies, scientists can create a model of how fast the universe is expanding. When these models are extrapolated backward, they yield an estimated age of approximately 13.8 billion years, a figure that has gained broad acceptance among cosmologists. These methods are cross-validated through various means, including observations from space telescopes and experiments like those conducted by the European Space Agency's Planck satellite. By consistently aligning findings from different approaches, scientists continue to refine their estimates and deepen our understanding of the cosmos. Ultimately, the age of the universe is not just a number, it's a gateway into the history of everything, from the formation of galaxies to the emergence of life on Earth. Cosmic microwave background radiation, often referred to as CMB, is essentially the faint glow left over from the Big Bang. This radiation fills the entire universe and is remarkably uniform, indicating that it originated when the universe was still in its infancy, about 380,000 years after the Big Bang. At that time, the universe cooled sufficiently for atoms to form, allowing photons to travel freely through space. This moment marked a crucial transitioning from an opaque state to one we can observe today. The significance of CMB lies in the information it provides about the early universe. By studying this ancient light, scientists can glean critical insights into the conditions that existed just after the universe began. The uniformity of the radiation suggests that the early universe was smooth, but tiny fluctuations in temperature can be observed. These fluctuations are key to understanding how matter was distributed shortly after the Big Bang, eventually leading to the formation of galaxies and large-scale structures we see today. Moreover, precise measurements of the CMB have revealed essential parameters of our universe, such as its age and composition. For instance, data from various missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite have helped establish that our universe is approximately 13.8 billion years old and consists primarily of dark energy and dark matter. This breakthrough deepens our understanding of the universe's evolution and fate. The cosmic microwave background serves as a cosmic relic, offering a snapshot of the universe's beginnings. It stands as one of the most compelling pieces of evidence supporting the Big Bang theory, allowing scientists to trace back the history of the cosmos and uncover the underlying dynamics that shape it. By analyzing CMB, researchers not only learn about our past, but also refine our predictions about the future of the universe. Technological advancements have revolutionized our understanding of the early universe, transforming what was once speculative science into a vibrant field of empirical knowledge. At the heart of this transformation lies the development of powerful telescopes and detectors that allow us to peer back in time, observing light that has traveled billions of years to reach us. Instruments like the Hubble Space Telescope have provided breathtaking images and valuable data, unveiling the formation of galaxies and the cosmic web that shapes our universe. Another key advancement is the rise of computer simulations and modeling. With increased computational power, scientists can simulate conditions of the early universe shortly after the Big Bang, exploring phenomena that would otherwise remain abstract. These simulations help us understand how matter and energy interacted, leading to the formation of the first stars and galaxies. They also allow us to test predictions of theoretical frameworks, such as inflation, which posits that the universe underwent a rapid expansion just moments after its inception. Moreover, advancements in particle physics and detectors have allowed us to recreate conditions akin to those in the early universe. Facilities like the Large Hadron Collider have enabled scientists to investigate fundamental particles and forces, shedding light on the building blocks of matter. By studying high-energy collisions, researchers glean insights into the behavior of particles shortly after the Big Bang, bringing us closer to unraveling the mysteries of cosmic evolution. Lastly, the advent of gravitational wave astronomy has opened new dimensions in our quest to understand the early universe. By detecting ripples in spacetime caused by massive cosmic events, such as colliding black holes, we gain fresh perspectives on phenomena that shape the universe. These discoveries not only enhance our understanding of cosmic history, but also reveal the intricacy of the universe's fabric, reaffirming just how much technology has deepened our grasp of our origins. Cosmic inflation is a theory that describes a dramatic and rapid expansion of the universe that occurred just after the Big Bang. Picture the universe as a balloon. In its infancy, this balloon underwent a period of explosive growth, ballooning from subatomic scales to cosmic scales in a fraction of a second, around a billionth of a trillionth of a second, to be precise. This period of inflation solved several mysteries of cosmology, including the uniformity of the universe and the existence of structure we see today. One of the most compelling implications of cosmic inflation is its explanation for the uniform temperature of the cosmic microwave background radiation. This radiation is a remnant of the Big Bang, a faint glow that fills the universe, and it appears remarkably uniform across vast distances. Inflation posits that regions now distant from each other were once close together, allowing the energy in those areas to equilibrate before rapid expansion pushed them apart. As a result, we observe this uniformity, along with the slight fluctuations that eventually gave rise to galaxies and clusters of galaxies. Inflation also provides insights into how the universe's large-scale structure was formed. The tiny quantum fluctuations present during this rapid expansion acted as seeds for the galaxies and stars that would form over billions of years. These primordial fluctuations grew under the influence of gravity, leading to the rich tapestry of structures in the universe we see today. Thus, cosmic inflation plays a crucial role in connecting the universe's earliest moments with the complex systems we observe in the cosmos now. Understanding cosmic inflation reshapes our view of the universe as not just expanding, but doing so from an extremely uniform and hot state to the vast, diverse cosmos filled with galaxies that we know today. It challenges our perceptions and enriches our grasp of the universe's origins, highlighting a fascinating chapter in the ongoing story of cosmic exploration. Through inflation, we gain a clearer picture of how the universe transitioned from simplicity to the complexity we observe now, offering a deeper appreciation for the intricacies of cosmic development. The universe is home to a vast array of galaxies, each with its own unique characteristics. The three primary types of galaxies are spiral, elliptical, and irregular. Each type exhibits distinct features shaped by their formation history and the gravitational interactions that govern their evolution. Spiral galaxies, like our Milky Way, are characterized by their beautiful, winding arms that extend from a central bulge. The arms contain stars, gas, and dust, giving them a vibrant appearance. These galaxies often host new star formation, indicated by blue regions where younger stars shine brightly. The spiral structure is maintained by the galaxy's rotation and the distribution of dark matter around it, which helps to keep the galaxy's shape intact over billions of years. Elliptical galaxies differ significantly from spirals. They tend to be more spherical or oval in shape and lack the prominent arms found in their spiral counterparts. These galaxies are usually older, consisting primarily of older stars and exhibiting little to no star formation. Their smooth and featureless appearance is a result of their star population's age and the absence of the gas and dust necessary for new stars to form. Irregular galaxies, as the name suggests, do not fit neatly into the other two categories. They display chaotic structures and are often rich in gas and dust, making them sites for vigorous star formation. These galaxies can be the result of gravitational interactions or collisions between galaxies which disrupt their shapes. As a result, they offer a unique glimpse into the dynamic processes at play in the universe's evolution, illuminating the paths galaxies can take throughout cosmic history. Time, clouds of gas and dust cooled and condensed, creating new stars and stellar systems. Many of these stars formed in clusters, and as they interacted gravitationally, they began to influence the surrounding material, leading to the development of a more structured galaxy. The structure of the Milky Way can be likened to a flat disk, with a central bulge, spiral arms, and a surrounding halo. The central bulge houses older stars and a supermassive black hole at its core, which is critical in holding the galaxy's mass together. Surrounding this bulge, the flat disk is where most of the Milky Way's stars reside, arranged in beautiful spirals. These spiral arms are sites of active star formation, where gas clouds collapse to form new stars, creating a dynamic landscape. The Milky Way's halo, on the other hand, extends far beyond the disk and bulge, containing older stars, globular clusters, and dark matter, which still remains mysterious. Dark matter's role is significant as it constitutes a large portion of the galaxy's total mass, influencing its gravitational structure without emitting light. This component is essential for understanding how galaxies like ours are held together and function. Understanding the formation and structure of the Milky Way not only sheds light on our cosmic neighborhood, but also helps physicists and astronomers explore the broader universe. It opens doors to critical questions about the origin of galaxies and the nature of the universe, revealing that we are part of a much larger cosmic tapestry. The story of our galaxy is a tale of cosmic evolution, marked by stellar births and deaths, all woven together in a grand display of astronomical beauty. The Milky Way galaxy, a vast swirl of stars, gas, and dust, formed about 13.6 billion years ago, shortly after the Big Bang. As matter in the universe began to clump together due to gravity, the first stars ignited, and these early stellar formations played a crucial role in the shaping of our galaxy. Over the Andromeda galaxy, known to scientists as M31, holds a special significance in our cosmic neighborhood as it is the nearest spiral galaxy to the Milky Way. Situated about 2.5 million light-years away, it represents a point of interest for astronomers seeking to understand the dynamics and evolution of galaxies. Andromeda and the Milky Way are not only close in proximity, but are also on a collision course that will unfold over the next few billion years. This impending collision has profound implications for both galaxies. When these vast collections of stars and interstellar material finally merge, they will likely form a new, larger galaxy. This event, often referred to as the Milky-Way merger, raises exciting questions about galactic evolution and the processes that govern star formation. The interactions between the two galaxies will lead to the reshaping of their structures, potentially triggering bursts of new star creation as gas clouds collide and collapse under gravity. Furthermore, studying Andromeda offers insights into the formation and behavior of galaxies similar to our own. By observing its structure, composition, and motion, scientists can draw parallels and distinctions between Andromeda and the Milky Way, helping to unravel the mysteries of how galaxies evolve over cosmic time. Andromeda contains around 1 trillion stars, a size that dwarfs our own Milky Way, which comprises about 200 billion stars. This stark difference invites curiosity about star density, distribution, and the potential for habitable systems within Andromeda. The Andromeda Galaxy is not just a neighboring celestial body, it serves as a vital key to understanding our universe on a larger scale. As we continue to explore Andromeda and monitor its movements, we deepen our understanding of cosmic history and the intricate dance that unfolds across the vast expanse of space. Galaxies, vast systems of stars, gas, dust, and dark matter can collide with one another due to their mutual gravitational attraction. As galaxies drift through the cosmos, often guided by the invisible pull of dark matter, they can find themselves on a collision course. This process is gradual, taking millions to billions of years. As two galaxies approach, their outer regions start to interact, stretching into long tidal tails while the gravitational forces begin to reshape their structures. The collision itself is not destructive in the way we might imagine, primarily because the distances between individual stars are immense. Most stars won't actually collide. However, the gas within galaxies can collide, triggering bursts of star formation. In the chaos of this interaction, celestial gas clouds can compress, leading to new stars and even forming beautifully intricate structures. For example, when the Milky Way is destined to collide with the Andromeda Galaxy in about 4 billion years, it is expected that star formation will surge as gas clouds collide. The consequences of galaxy collisions extend beyond mere star formation. These interactions can lead to the merging of galaxies, resulting in new galactic formations that can take on distinct shapes. Over time, the galaxies may settle into a stable arrangement, often becoming elliptical galaxies, less conducive to new star formation compared to their spiral predecessors. Such mergers can also drive the growth of supermassive black holes at the centers of these galaxies, as they feed off the increased gas and stars available during and after the collision. Moreover, these galactic collisions can provoke profound changes in the universe itself. They contribute to the cosmic evolution, shaping the cosmic web that dictates the distribution of galaxies across vast distances. Each collision tells a story of galactic growth and transformation, reminding us of the continuous, dynamic nature of the universe, where nothing is ever truly static. In the grand ballet of existence, galaxy collisions are but one of the many intricate moves that highlights the beauty and complexity of the cosmos. Dark matter and dark energy are two of the most significant yet mysterious components of the universe. Together, they make up around 95% of the cosmos, yet elude direct detection. Dark matter, which accounts for roughly 26%, is an invisible substance that interacts with regular matter through gravity but does not emit light or energy. Its presence is inferred from the way galaxies rotate and how they cluster together. This unseen mass helps hold galaxies in their gravitational embrace, acting like a cosmic glue. Without dark matter, the universe as we know it would not exist. The stars and galaxies would drift apart, unable to maintain their structure. On the other hand, dark energy constitutes about 69% of the universe and has a very different role. Discovered through observations of distant supernovae, dark energy is driving the accelerated expansion of the universe. While dark matter pulls matter together, dark energy pushes it apart. This counterintuitive force affects the universe on the largest scales and is believed to be responsible for the current acceleration of cosmic expansion, shaping the future of galaxies and the universe itself. Understanding these two components is crucial for astronomers and cosmologists as they explore the intricacies of galaxy formation and evolution. The properties of dark matter influence the distribution of galaxies in clusters, guiding our understanding of how these celestial bodies formed in the early universe. Meanwhile, dark energy presents fundamental questions about the fate of the universe, challenging scientists to rethink models of cosmology and the ultimate destiny of everything from stars to galactic clusters. Dark matter and dark energy are not just ambiguous terms in a glossary of cosmological phenomena. They represent the very fabric of the universe, intricately woven into the histories and dynamics of galaxies. As researchers continue their quest to comprehend these enigmatic forces, they open doors to deeper insights into the workings of the cosmos and our existence within it. Scientists searching for and studying galaxies billions of light-years away rely on a combination of powerful telescopes and advanced imaging techniques. The vast distances in the universe mean that light takes a very long time to reach us, with the light we see from a galaxy billions of light-years away actually being emitted billions of years ago. This means that when astronomers observe these distant galaxies, they are looking back in time, gaining insights into the early stages of galaxy formation and evolution. Telescopes, particularly those situated in space, play a crucial role in this quest. Instruments like the Hubble Space Telescope and the recently launched James Webb Space Telescope can capture light from faraway galaxies by utilizing advanced sensors and imaging technology. These telescopes are designed to detect not just visible light, but also infrared and ultraviolet radiation, allowing scientists to gather a broader spectrum of data. This capability is essential, as many distant galaxies emit light that is redshifted due to the expansion of the universe, meaning their light has shifted toward the red end of the spectrum. Moreover, astronomers combine observations from different wavelengths to build a more comprehensive picture. For instance, infrared observations can reveal how galaxies formed and evolved, while ultraviolet light provides information about the star formation rates and the presence of young stars. By analyzing these different datasets, scientists can piece together a timeline of galaxy development and assess their compositions and structures. Additionally, advances in computer modeling and simulation allow scientists to recreate the conditions and processes that led to the formation of these galaxies. Through this combination of observational astronomy and theoretical work, researchers continuously refine our understanding of the cosmos, uncovering the mysteries of how galaxies evolve over billions of years in the vast expanse of space. Each discovery offers a glimpse into our universe's history, captivating all who ponder the questions of our place within it. A black hole is an incredibly dense region in space where the gravitational pull is so strong that nothing, not even light, can escape from it. This phenomenon occurs when a massive star exhausts its nuclear fuel and can no longer support itself against gravitational collapse. When this happens, the star's core is crushed to an unimaginably small point known as a singularity, surrounded by an event horizon, the boundary beyond which nothing can return. The process of black hole formation begins in the life cycle of a massive star. For stars that start out with a mass more than about 20 times that of our Sun, they eventually enter a stage called supernova, a colossal explosion that signifies the end of the star's life. During this explosion, the outer layers of the star are blown away, while the core collapses under its own gravity, leading to the formation of a black hole. Interestingly, not all black holes form from the deaths of massive stars. Some black holes may be born from the merging of neutron stars, which are even denser remnants of supernova events. In this case, when two neutron stars spiral toward each other and combine, they can create a black hole through their intense gravitational forces. Astronomers have detected gravitational waves, ripples in spacetime, created by such cosmic collisions, giving us a fascinating glimpse into the universe's dynamic processes. Today, we know of various types of black holes, including stellar black holes, which are several times more massive than the Sun, and supermassive black holes that reside at the centers of galaxies, with masses equivalent to millions or even billions of suns. The mysteries that surround black holes captivate both scientists and enthusiasts alike, as they challenge our understanding of physics and the fundamental nature of reality. Black holes are some of the most fascinating and extreme objects in the universe, exerting a profound influence on the fabric of space and time around them. At the core of their dramatic effect is a concept rooted in Einstein's theory of general relativity, which visualizes gravity as a curvature of space-time. When a massive star collapses into a black hole, it creates an intense gravitational pull that warps the surrounding space-time, much like a heavy object placed on a taut rubber sheet. As one moves closer to a black hole, this curvature of space-time becomes increasingly pronounced. The region surrounding a black hole is known as the event horizon, which is the point of no return. Once something crosses this threshold, it cannot escape the black hole's grasp. This distortion has fascinating implications for time itself. Observers far away from a black hole would notice that time near the event horizon moves more slowly compared to distant regions of space. This effect, known as time dilation, showcases how deeply black holes can manipulate the passage of time alongside the geometry of space. Furthermore, black holes can influence their surroundings beyond the immediate effects of their gravitational pull. They can drive the accretion of surrounding gas, creating powerful jets of particles that shoot outwards at nearly the speed of light. These jets can reshape nearby materials, creating environments that can affect star formation and galactic evolution. This interplay of energy and gravity creates dynamic systems as matter spirals inward, heating up and emitting radiation that can be detected across vast distances. Black holes are gateways to understanding the universe's most extreme phenomena. They challenge our perception of reality as they remind us that mass and gravity can warp the very structure of space and time itself. As researchers continue to observe these celestial giants, we uncover new insights into the fundamental laws that govern our universe, revealing the beauty and complexity of nature's design. The event horizon is a crucial concept in the study of black holes. It can be understood as an invisible boundary surrounding a black hole beyond which no information or matter can escape. Once something crosses this threshold, it cannot return to the outside universe. This unique feature makes black holes fascinating objects of study in astrophysics as they challenge our understanding of gravity and the nature of time and space. The significance of the event horizon lies in its relationship to the immense gravitational pull exerted by black holes. As an object approaches this boundary, it experiences extreme tidal forces. The intensity of gravity near the event horizon warps space and time, creating conditions that are radically different from those in our familiar universe. For scientists, the event horizon represents not just a limit to what we can observe, but also a gateway to understanding fundamental physics. Moreover, the event horizon plays a vital role in the process of information loss associated with black holes. When stars and gas fall into a black hole, the information about their properties seems to be lost forever, leading to heated debates among physicists. This question touches on the fundamental principles of quantum mechanics and general relativity, pushing researchers to find a unified theory that can explain phenomena at both the cosmic and quantum scales. The event horizon is much more than a mere boundary. It defines the region of no return in a black hole's environment and introduces challenges to our existing theories of physics. Studying this enigmatic feature allows scientists to explore some of the deepest questions about the universe, from the nature of gravity to the interplay between information and reality. Black holes, by their very nature, are fascinating cosmic entities that do not emit light, making them invisible to traditional observation methods. However, scientists have developed clever techniques to detect and measure these mysterious objects through indirect evidence. One of the primary ways to spot a black hole is by observing its effects on nearby stars and gas. When a star orbits a black hole, it often moves in a unique pattern that indicates the presence of an unseen massive object. By measuring this motion, astronomers can estimate the black hole's mass. Another critical method involves the examination of the intense radiation emitted from the accretion disk surrounding a black hole. As matter spirals in toward the event horizon, it accelerates and heats up, generating significant amounts of X-rays and other forms of energy. Telescopes equipped to detect X-ray emissions, like the Chandra X-ray Observatory, can identify these hot, glowing regions. If we see an area in space emitting notable X-rays without a visible star nearby, it can often suggest the presence of a black hole. Gravitational waves also play a vital role in the study of black holes. When two black holes collide, they create ripples in spacetime known as gravitational waves. Detectors such as LIGO and Virgo can pick up these waves, allowing scientists to infer details about the black holes involved in the collision, including their masses and spin. This groundbreaking method has opened a new window into the study of not just black holes, but the fundamentals of the universe itself. These innovative detection methods reflect the ingenuity of scientists as they strive to understand what exists beyond our view. Through careful observation of gravitational effects, high-energy emissions, and cosmic events, we gain a glimpse into the nature of black holes, enhancing our understanding of the universe's most enigmatic features. The quest to reveal the secrets of black holes continues as we advance our technologies and deepen our knowledge of the cosmos. Supermassive black holes are colossal entities, weighing millions to billions of times the mass of our Sun. They reside at the centers of most galaxies, including our own Milky Way, and their formation is still a subject of intense research. These black holes grow by consuming surrounding gas and dust, merging with other black holes and absorbing stars that wander too close. This immense gravitational pull allows them to reign over their galactic neighborhoods. Their influence extends far beyond their immediate vicinity, affecting the structure and evolution of their host galaxies. The energy output from materials spiraling into a supermassive black hole can be staggering, often resulting in the formation of powerful jets and radiation that can illuminate the cosmos. This energetic activity heats the surrounding gas and can induce powerful winds, which can prevent the formation of new stars. In many cases, the life cycles of galaxies are intertwined with the dynamics of their supermassive black holes, showcasing a fascinating cosmic symbiosis. Recent studies suggest a correlation between the mass of supermassive black holes and the properties of their host galaxies, particularly the velocity of stars in the galactic center. This relationship hints at a shared evolutionary path. When a supermassive black hole grows and becomes more active, it may simultaneously influence star formation rates and the overall stellar content of the galaxy. As a result, galaxies can take on distinct forms and behaviors shaped by the unseen forces at their core. Ongoing research continues to uncover the nuances of this relationship. As we refine our understanding of supermassive black holes, we gain insights into the past and future of galaxies themselves. They are not merely gravitational monsters, they are key players in the grand narrative of cosmic evolution, shaping not just their homes, but perhaps even the structure of the universe as a whole. Black holes have long fascinated astronomers and physicists, primarily because their interiors challenge our understanding of the universe. At the heart of a black hole lies a region called the singularity. Here, according to current theories, gravitational forces become so intense that they warp spacetime to the point where the known laws of physics cease to function reliably. The singularity represents a point of infinite density, where everything that has fallen into the black hole is crushed to an unimaginable point. Beyond the singularity, there are various theoretical models that attempt to describe what might lie inside a black hole. One prominent idea is the no-hair theorem, which suggests that black holes can be completely described by just three properties: mass, electric charge, and angular momentum. This implies that all other information about the matter that formed or fell into the black hole is lost, leaving a simple entity present inside. However, some scientists propose that information might not be lost, but rather hidden in a complex way. The notion was popularized by the physicist Stephen Hawking, who introduced the concept of Hawking radiation. This radiation suggests that black holes could gradually leak information as they emit energy, which can ultimately result in their evaporation. This leads to intriguing implications about the fate of information in the universe and whether it can be recovered or simply disappears forever. Another interesting theory is the idea of wormholes. Some physicists theorize that black holes might connect distant parts of the universe or even different universes altogether through these hypothetical tunnels in spacetime. While these ideas remain speculative, they inspire both scientists and public imagination about the deeper mysteries of black holes. As our tools and theories develop, the quest to unveil the secrets hidden within these cosmic enigmas continues to ignite curiosity about our universe. The birth of a star begins in the heart of a molecular cloud, a vast region of space filled with gas and dust. Within these clouds, regions of higher density can become gravitationally unstable, causing them to collapse under their own weight. As the material gathers, it forms a protostar, where gravity pulls the surrounding gas and dust into a spinning disk. This process is accompanied by an increase in temperature, and within just a few million years, nuclear fusion ignites at the core, marking the transition from a protostar to a main sequence star. Main sequence stars, which include our Sun, spend the majority of their lives fusing hydrogen into helium in their cores. This phase can last for billions of years, depending on the star's mass. Smaller stars, like red dwarfs, have a cooler surface temperature and burn their hydrogen slowly, while larger stars consume their fuel much faster. As they age, these stars will eventually exhaust the hydrogen in their cores, leading to significant changes in their structure and behavior. Once a star runs out of hydrogen, it embarks on a journey through various stages. For moderate mass stars, this leads to the expansion into a red giant where helium is fused into heavier elements. After this phase, these stars encounter a dramatic end, shedding their outer layers and leaving behind a dense core called a white dwarf. In the case of massive stars, the end is even more explosive. They may go supernova, a cataclysmic explosion that results in either a neutron star or a black hole, depending on the remaining mass. The life cycle of a star is a remarkable process that shapes the very fabric of the universe. From the gas and dust of a collapsing cloud to the energetic explosions marking the end of a massive star, each stage plays a crucial role in the cosmic ecosystem. This cycle not only forms the stars and planets we see today, but also disseminates essential elements, enriching the interstellar medium and paving the way for new generations of stars and worlds to emerge. A star's lifespan and ultimate fate are primarily determined by its mass, composition, and the way it generates energy. The most significant factor is mass. The greater a star's mass, the faster it consumes its nuclear fuel. Massive stars can burn through their hydrogen reserves in just a few million years, while smaller stars, like our Sun, can thrive for billions of years. This difference in lifespan is a result of how quickly the star's core temperatures and pressures rise, leading to rapid fusion processes. The composition of the star also plays a crucial role. Stars are made mostly of hydrogen and helium, but the presence of heavier elements influences how they evolve. For example, stars with higher metallicity can form dust and planetary systems more readily than those made up primarily of hydrogen. These differences affect not only their lifetimes, but also the types of byproducts they produce at the end of their life cycles. As stars exhaust their fuel, they undergo dramatic changes. A low to intermediate mass star like the Sun will expand into a red giant, shed its outer layers, and leave behind a hot core that becomes a white dwarf. In contrast, massive stars can explode in a supernova after forming a neutron star or even collapse into a black hole. This catastrophic end is a fascinating glimpse into how the universe recycles matter, creating the building blocks for new stars and planets. The lifespan and fate of a star are governed primarily by mass and composition, with their unique evolutionary paths showcasing the dynamic processes at play in the cosmos. As they burn bright, they contribute to the tapestry of the universe, influencing everything from the formation of elements to the ongoing cycle of star birth and death. Measuring the size and composition of distant stars is a fascinating challenge that scientists have devised clever methods to tackle. One of the primary techniques for understanding a star's size is through a method called stellar parallax. This approach involves observing a star from two different points in Earth's orbit around the Sun. By measuring the apparent shift in position against more distant background stars, scientists can calculate the distance to the star. With this distance known, they can employ additional methods to estimate the star's size, often using its brightness and temperature. Another key method for determining a star's size is through the analysis of its brightness, known as its luminosity. By employing the inverse square law of light, scientists can estimate how far away a star is by measuring the amount of light that reaches Earth. Once distance is established, astronomers can compare the observed brightness to the intrinsic brightness of similar stars to gauge size. If a star is particularly large and bright, its enormous energy output signals that it must indeed be a giant in the universe. In terms of composition, scientists rely heavily on spectroscopy. By dispersing a star's light into a spectrum, they can identify the unique fingerprint of elements the star contains. Each element absorbs and emits light at specific wavelengths, allowing astronomers to determine what materials are present. By examining these spectral lines, scientists can infer not only the star's chemical makeup, but also its temperature, density, mass, and even its age. Finally, advanced telescopes, including space-based observatories like the Hubble Space Telescope, have enhanced our ability to measure both the size and composition of distant stars with greater accuracy. With these tools, astronomers continuously refine their understanding of our universe, revealing a cosmic tapestry of stars that varies vastly in size, age, and composition. Through these dedicated efforts, we inch closer to unraveling the mysteries of the stars that light up our night sky. Neutron stars are the remnants of massive stars that have exhausted their nuclear fuel and undergone a supernova explosion. When such a star collapses under its own gravity, it compresses protons and electrons together to form neutrons, leading to an incredibly dense object. A single teaspoon of neutron star material could weigh as much as 5 billion tons, highlighting the extreme conditions found in these celestial bodies. Despite their small size, typically around 20 kilometers in diameter, they possess a mass greater than that of our Sun. Pulsars are a special type of neutron star that emit beams of electromagnetic radiation, often observed as pulses. These beams are generated due to the star's rapid rotation and strong magnetic fields. As a pulsar spins, the magnetic poles of the neutron star sweep across the sky. If the beam is directed toward Earth, we see a pulse of radiation with incredible precision. Some pulsars rotate hundreds of times a second, making them some of the most stable natural clocks in the universe. What makes neutron stars and pulsars unique extends beyond their density and rotation. They also provide insights into fundamental physics. The extreme gravitational forces in neutron stars push the laws of physics to their limits, offering opportunities to study matter under conditions that cannot be replicated on Earth. Scientists are especially intrigued by how matter behaves at such high densities, which challenges existing models of particle interactions and the fabric of space and time itself. Moreover, pulsars serve as vital tools for astronomers. Their predictable pulses can be used to measure cosmic distances and investigate gravitational waves. Observations of these enigmatic stars have unfurled a wealth of knowledge about the universe and its fundamental aspects, deepening our understanding of the life cycle of stars and the nature of gravity, thus continuing to inspire a sense of wonder about the cosmos. Binary star systems consist of two stars that orbit around a common center of gravity, bound together by their mutual gravitational attraction. These stars can be in various configurations. They can be close together or far apart, and their orbits can be circular or elliptical. In many cases, these systems are so closely linked that one star's influence can significantly affect the other's evolution, brightness, and even its ultimate fate. This close interaction often leads to fascinating phenomena, such as one star siphoning material from its companion, altering the dynamics in surprising ways. The allure of binary star systems lies in the insights they provide into stellar evolution. By observing these stars, astronomers can gather data on their masses, sizes, and temperatures, which are critical for understanding how stars form and develop over time. Mass is particularly important as it dictates a star's life cycle. Larger stars burn through their fuel rapidly, while smaller stars can last many billions of years. This direct relationship means that studying binary systems allows us to assess stellar mass in ways that isolated stars simply cannot provide. Another reason astronomers find these systems compelling is the potential for discoveries of exoplanets and unique cosmic events. For instance, eclipsing binaries, where stars pass in front of one another from our perspective, can reveal the sizes and characteristics of the stars involved. Furthermore, these stars can exhibit exotic behaviors, like when one star enters a supernova phase, providing critical information about stellar death and the subsequent formation of neutron stars or black holes. The study of binary stars also raises questions about the makeup of our universe, especially with phenomena like gravitational waves generated by the merger of binary neutron stars. These events not only produce ripples in spacetime, but also create heavy elements such as gold and platinum, which are vital to the makeup of our own planet. As astronomers continue to explore binary systems, we gain deeper understanding of the cosmos, unveiling the intricate relationships and processes that govern the life cycles of stars and the universe itself. Supernovae are not just spectacular cosmic explosions. They play a crucial role in the life cycle of stars and the evolution of the universe. When a massive star reaches the end of its life, it exhausts the nuclear fuel that has been sustaining its energy output. Without this fuel, the inward gravitational pull outweighs the outward pressure from nuclear fusion, causing the star's core to collapse. This collapse triggers a catastrophic explosion, releasing an immense amount of energy in the form of a supernova. The energy released by a supernova can briefly outshine an entire galaxy. During this powerful event, heavy elements are created and enriched in the stellar environment. Elements like iron, nickel, and even heavier ones such as gold and uranium are formed in the high-energy conditions of the explosion. Once these elements are scattered into space, they contribute to the next generation of stars and planets, participating in the complex processes of cosmic recycling. Supernovae also play an important role in the dynamics of galaxies. The shock waves generated by these explosions can trigger the formation of new stars by compressing nearby gas clouds. This feedback mechanism influences the rate of star formation in galaxies, showing that supernovae are not merely destructive events, but can also catalyze new beginnings. Moreover, studying supernovae helps astronomers understand the expansion rate of the universe. For instance, observations of distant supernovae have provided key insights into the acceleration of cosmic expansion, leading to the discovery of dark energy. Thus, supernovae are not only pivotal in the life cycle of stars, but are also fundamental to our understanding of the large-scale structure and evolution of the cosmos. A planet is generally defined by a few key characteristics that distinguish it from other celestial bodies. To qualify as a planet, an object must orbit a star, maintain sufficient mass to achieve a nearly round shape due to its own gravity, and have cleared its orbit of other debris. This last criterion is particularly significant because it emphasizes a planet's dominance in its orbital neighborhood, a characteristic that some bodies, like Pluto, no longer meet after being reclassified as a dwarf planet. Within our solar system, the planets exhibit a remarkable diversity that highlights their unique evolutionary histories. The 8 recognized planets can be broadly categorized into 2 groups: terrestrial planets and gas giants. The terrestrial planets, which include Mercury, Venus, Earth, and Mars, are rocky and have solid surfaces. They are characterized by their smaller sizes and higher densities. For instance, Earth, with its rich atmosphere and abundance of liquid water, stands apart as a unique environment for life. On the other hand, the gas giants, Jupiter and Saturn, along with the ice giants, Uranus and Neptune, are vastly different. These larger planets are composed mainly of gases and ices lacking solid surfaces. Jupiter, the largest planet in our solar system, exemplifies the gas giant category, boasting a thick atmosphere and an iconic Great Red Spot, a massive storm that has persisted for centuries. Meanwhile, ice giants like Uranus and Neptune offer a fascinating glimpse into atmospheric extremes, with deep, frigid interiors and dynamic weather systems. The differences among the planets in our solar system create a rich tapestry of environments that have not only captivated scientists, but also sparked the imagination of humankind. From the boiling surface of Venus to the icy rings of Saturn, each planet provides unique insights into the formation and evolution of our cosmic neighborhood. Understanding these characteristics allows us to appreciate the complexity of planetary systems both within and beyond our solar system, fueling the quest for knowledge about the universe we inhabit. The discovery and study of exoplanets, worlds that orbit stars beyond our solar system, represents one of the most exciting frontiers in modern astronomy. Scientists employ a variety of methods to identify these distant planets, each providing unique insights into their properties and the conditions that might support life. One of the most prominent techniques is the transit method. This approach involves monitoring the brightness of a star over time. When a planet passes in front of the star, it blocks a small fraction of the star's light, causing a temporary dip in brightness. This subtle change allows astronomers to confirm the presence of an exoplanet and even estimate its size. Another significant method is the radial velocity technique, sometimes called the Doppler method. This involves measuring the star's spectrum. As a planet orbits its star, the gravitational pull induces a slight wobble in the star's position. This motion affects the light from the star, shifting it toward red or blue in a phenomenon called redshift and blueshift. By analyzing these shifts, scientists determine the presence of a planet and can estimate its mass, offering hints about its composition and potential habitability. Telescopes equipped with advanced technology, including space-based observatories like the Kepler Space Telescope and the Transiting Exoplanet Survey satellite, have played a crucial role in advancing our understanding of exoplanets. Kepler alone has discovered thousands of exoplanets, expanding our knowledge of planetary systems throughout the galaxy. These missions utilize precise instruments for detecting slight changes in light and measuring various stellar attributes, helping astronomers identify a wide range of planetary types and sizes, from gas giants to rocky worlds. As our observational technologies improve, scientists are not only discovering more exoplanets, but are also beginning to study their atmospheres and compositions. By examining how starlight filters through an exoplanet's atmosphere during a transit, researchers can learn about the gases present and research the potential for supporting life. With each passing year, astronomers edge closer to answering the tantalizing question: are we alone in the universe? The search for Earth-like exoplanets has yielded some fascinating discoveries that expand our understanding of the cosmos. Among these, a few stand out, particularly those found in the habitable zones of their stars, where conditions may be just right for liquid water to exist. One remarkable candidate is Proxima Centauri b, orbiting the closest star to our Sun, Proxima Centauri. This exoplanet resides within its star's habitable zone, indicating the potential for temperatures that could support liquid water. Its proximity at just over 4 light-years makes it particularly intriguing for future exploration. Another notable example is Kepler 186f, part of a system located about 511 light-years away. Kepler 186f is about 1.5 times the size of Earth, and importantly, it orbits within the habitable zone of a faint red dwarf star. The discovery of this exoplanet was significant because it was the first time astronomers identified a planet that is roughly Earth-sized and positioned in a region where conditions could allow for the presence of liquid water. Then there's TRAPPIST-1, a fascinating star system that contains 7 Earth-sized planets, several of which dwell in the habitable zone where temperatures could allow for liquid water to exist. Located around 40 light-years from Earth, TRAPPIST-1 has garnered considerable attention due to its potential for habitability. These planets are especially appealing because they orbit a cooler star, which allows for closer orbits without subjecting them to harsh radiation, thus creating an environment ripe for life as we know it. Finally, Gliese 581g is another contender in this exclusive club. While there is some debate about its existence, Gliese 581G orbits its star within the habitable zone and has sparked interest due to its Earth-like characteristics. Each of these exoplanets contributes uniquely to our understanding of what worlds beyond our own might look like and where we may one day find signs of life. Our continuing exploration of these distant planets reminds us that the universe is full of possibilities waiting to be unveiled. Planetary atmospheres in our solar system exhibit an astounding range of characteristics, influenced by various factors like proximity to the Sun, planetary composition, and geological activity. For instance, Earth's atmosphere is a rich mixture of nitrogen and oxygen, creating a perfect environment for life. In contrast, Venus boasts a thick atmosphere dominated by carbon dioxide, with clouds of sulfuric acid. This results in a runaway greenhouse effect, leading to surface temperatures that can melt lead. Mars presents another stark contrast. Its atmosphere is thin and primarily carbon dioxide, with only traces of other noble gases. This sparse atmosphere contributes to the planet's cold surface temperatures and the absence of substantial water bodies. Additionally, the lack of a strong magnetic field exposes Mars to solar winds, stripping away much of its atmosphere over billions of years. Further out, gas giants like Jupiter and Saturn display massive layers of hydrogen and helium, along with powerful storms and high-speed winds. Jupiter's Great Red Spot, a storm larger than Earth, illustrates the dynamic nature of these atmospheres. In comparison, the icy giants, Uranus and Neptune, contain similar elements but exhibit distinct winds and weather patterns, likely due to different internal heat sources and compositions. Beyond our solar system, exoplanets showcase even more diverse atmospheric conditions as astronomers discover worlds with atmospheres rich in exotic gases. Some exoplanets orbit their stars at such close ranges that their atmospheres reach extreme temperatures, creating vaporized atmospheres composed of elements like sodium and potassium. This ongoing exploration highlights the incredible variety of planetary atmospheres and the myriad of conditions that exist across the universe, opening new frontiers in our understanding of chemistry, climate, and potentially habitable environments. The discovery of water on other planets or moons is a groundbreaking development in the field of astrobiology and planetary science. Water is critical for life as we understand it. Finding it beyond Earth opens up exciting possibilities regarding the existence of extraterrestrial life. Scientists believe that if life did emerge on other worlds, it would likely require water, which acts as a solvent for biochemical reactions essential for life. In addition to its implications for the search for life, water is also significant for future human exploration. If we are to establish human settlements on other planets or moons, access to water would provide a vital resource not only for drinking and hygiene, but also for growing food. Furthermore, water can be broken down into hydrogen and oxygen, which could be used as rocket fuel. This makes locations with water highly attractive for long-term exploration and habitation. The search for water has led to remarkable discoveries. For example, scientists have confirmed the presence of ice on Mars and discovered vast oceans beneath the crust of Europa, one of Jupiter's moons. Observations from telescopes have even detected signs of water vapor in the atmospheres of exoplanets, hinting that water may be more common in the universe than previously thought. These findings contribute to a growing understanding of the potential habitability of other celestial bodies. Overall, the significance of finding water on other planets or moons spans both the quest for extraterrestrial life and the prospects for human exploration. It propels our understanding of how life could exist elsewhere and informs strategies for future missions, ensuring that our journey into the cosmos is both thoughtful and transformative. Gas giants and rocky planets represent two distinct categories of planets within our solar system and beyond, each with their own unique characteristics. Gas giants, which include Jupiter, Saturn, Uranus, and Neptune, are primarily composed of hydrogen and helium. Their massive atmospheres create an environment that lacks a well-defined solid surface, leading to their classification as gas giants. In contrast, rocky planets, also known as terrestrial planets such as Mercury, Venus, Earth, and Mars, have solid, rocky surfaces made up of metals and silicate materials. One of the most significant differences lies in their physical structure. Gas giants have deep atmospheres filled with thick clouds and intense storms. For instance, Jupiter is home to the Great Red Spot, a gigantic storm that has been raging for centuries. In contrast, rocky planets have a hard surface with varied geological features such as mountains, valleys, and craters, shaped by volcanic activity and erosion. Earth, with its dynamic tectonic plates, showcases a diverse landscape and enables the presence of life, something not found on the other rocky planets. The composition also differs dramatically. Gas giants have a relatively small, rocky core surrounded by an extensive atmosphere. They may have liquid metallic hydrogen and surrounding icy layers further out. In contrast, rocky planets have a more uniform structure with a core made of metals like iron and a mantle composed of silicate rocks topped by a crust where life can thrive. This geological makeup results in very different atmospheres. For example, Venus has a thick, toxic atmosphere of carbon dioxide that creates extreme greenhouse conditions, whereas Earth has a balanced atmosphere conducive to life. Lastly, the formation process distinguishes these two types of planets. Gas giants typically form in the colder regions of a protoplanetary disk, allowing them to accumulate large amounts of gas as they grow. Rocky planets form in warmer areas, where solid materials can clump together to create their dense, rocky structures. Each type plays a crucial role in the overall architecture of our solar system and continues to be a focal point for astronomers seeking to understand planetary formation and the potential for life beyond Earth. The formation of our solar system is a fascinating journey that begins with a vast cloud of gas and dust known as a solar nebula about 4.5 billion years ago. This nebula, composed primarily of hydrogen and helium, began to collapse under its own gravity, possibly triggered by shock waves from nearby supernovae. As the nebula contracted, it began to spin, and in this process, it flattened into a rotating disk. In the center of this disk, material gathered to form the Sun. Over time, the intense heat and pressure of the forming star initiated thermonuclear fusion, sparking the birth of our Sun. Meanwhile, within the surrounding disk, particles started to collide and stick together. This process, known as accretion, led to the formation of planetesimals, small bodies that would become the building blocks of planets. Through further collisions and gravitational interactions, these planetesimals coalesce to form the planets, moons, asteroids, and comets we recognize today. One of the key theories explaining the current configuration of the solar system is the NICE model. This theory suggests that after the planets formed, they settled into stable orbits. However, interactions between the giant outer planets, Jupiter, Saturn, Uranus, and Neptune, eventually led to a massive rearrangement. This model proposes that the planets migrated in their orbits over millions of years, with gravitational interactions causing Saturn and Jupiter to swap places, dramatically influencing the distribution of smaller bodies in the solar system. Another significant aspect of our solar system's configuration is the distinction between the inner rocky planets, Mercury, Venus, Earth, and Mars, and the outer gas giants. This division can be attributed to the solar nebula's temperature gradient. The inner regions were hotter, leading to the formation of terrestrial planets, while the cooler outer regions allowed gas giants to form, gathering thick envelopes of gas and ice. Together, these theories help us understand not only how our solar system came into being, but also why it has taken its current form, filled with diverse worlds that continue to capture our imagination. The solar system is a complex and dynamic environment composed of various elements that continually interact with one another. One of the primary factors contributing to its ever-changing nature is gravitational interactions. The immense mass of the Sun exerts a gravitational pull that governs the orbits of planets, moons, and smaller bodies like asteroids and comets. This gravitational influence can lead to changes in orbital paths, which can, over time, result in dramatic shifts in distance, speed, and even the potential for collisions among celestial objects. Another significant factor is the presence of celestial phenomena such as comets, meteoroids, and asteroid belt dynamics. These smaller bodies can be nudged by gravitational forces, altering their orbits. When these objects travel into the inner solar system, they can become active comets, displaying glowing tails as they approach the Sun due to the sublimation of their icy components. Additionally, the threat of impact events on planets, particularly Earth, reminds us of the delicate balance and ongoing changes taking place in our solar neighborhood. The solar cycle itself also plays a role in the dynamic nature of the solar system. This cycle, lasting about 11 years, sees fluctuations in solar radiation and magnetic activity. During periods of heightened solar output, known as solar maximum, the Sun produces intense solar flares and coronal mass ejections. These phenomena can influence the space weather environment, affecting satellites, radio communications, and even power grids on Earth, demonstrating how solar activity directly impacts our daily lives. Lastly, the gradual evolution of planets and moons due to geological processes adds an additional layer of dynamism. Tectonic activity, volcanic eruptions, and erosion can reshape planetary surfaces over millions of years. The moons of gas giants like Jupiter and Saturn showcase their own dynamic processes. For instance, Io is famous for its extreme volcanic activity, a result of tidal forces exerted by its massive planetary companion. The solar system is in a constant state of change, shaped by gravitational dynamics, celestial bodies, solar activity, and geological processes, making it a fascinating tapestry of cosmic evolution. Comets and asteroids play a significant role in shaping the dynamics of our solar system and have impactful consequences for life on Earth. These celestial bodies are remnants from the early formation of the solar system, acting like time capsules that hold clues to its origins. Their presence has provoked both questions and fears throughout history, mainly due to their potential to collide with planets. Such events have been pivotal in Earth's evolutionary journey, often leading to mass extinctions and the subsequent emergence of new species. One of the most infamous examples of this influence is the asteroid impact that occurred approximately 66 million years ago. This event is widely believed to have caused the extinction of the dinosaurs. A massive asteroid struck what is now the Yucatan Peninsula in Mexico, leading to dramatic climate changes that eradicated about 75% of all life on Earth. Such catastrophic events illustrate how the dynamics of celestial bodies can dramatically alter the course of life on our planet. On the flip side, comets, which are primarily composed of ice and dust, have also contributed significantly to the development of life. When comets collide with Earth, they may deliver water and organic compounds, the essential building blocks for life. Scientific theories suggest that the early bombardment of Earth by these icy bodies could have provided the necessary elements for life to emerge. This process raises fascinating questions about the origins of life and whether other celestial bodies might harbor similar potential for life. Beyond their direct impacts on Earth, comets and asteroids influence the gravitational interplay within the solar system. These objects can alter orbits and affect the stability of celestial bodies, which ultimately shapes the environment of planets. Understanding their journeys through space helps astronomers predict potential threats and informs us about the evolutionary history of our solar system. The dance of comets and asteroids reminds us that our place in the universe is ever-changing, and their legacy continues to shape not only our planet, but the future of life itself. The search for Planet 9 has captivated the scientific community and the public alike. Although it remains elusive, its existence is suggested by unusual gravitational effects observed in the outer solar system. Astronomers have noted that several distant objects exhibit peculiar orbits, which cannot be fully explained by the gravitational influence of known planets. This raises the tantalizing possibility that a massive yet unseen planet is lurking in the far reaches of our solar system. One of the most intriguing aspects of Planet 9 is its potential characteristics. If it exists, it could be many times the mass of Earth and situated far beyond Neptune, possibly taking between 10,000 to 20,000 years to complete a single orbit around the Sun. This theoretical planet could be providing a gravitational tug that shapes the paths of these distant objects, acting almost like an invisible shepherd in the cosmic wilderness. Yet, the evidence remains circumstantial. Searches that have scoured the skies have yet to definitively confirm Planet 9's presence. Telescopes and surveys continue to look for signs of its existence, but the vastness of space presents substantial challenges. Each new discovery of celestial bodies in the outer solar system raises questions, but also highlights our limited understanding of the dynamics at play. Beyond Planet 9, the search for other hypothetical planets also stirs excitement in the field of astronomy. The Kuiper Belt, a region filled with icy bodies past Neptune, may host additional, yet-to-be-discovered planets. Additionally, some theories even posit that our solar system may have originally harbored more planets, which were ejected due to gravitational interactions. As the quest continues, the mysteries surrounding Planet 9 and its companions remind us of the uncharted territory that still fuels our exploration of the cosmos. The Moon, Earth's only natural satellite, has exerted a profound influence on our planet's development throughout history. One of the most significant impacts is its role in stabilizing Earth's axial tilt. This stability helps regulate our climate and seasons, making this planet a suitable home for life. Without the Moon, Earth's tilt could vary more dramatically, leading to extreme changes in climate that could disrupt the delicate balance necessary for life to thrive. Moreover, the Moon has played a critical part in shaping the tides. The gravitational pull of the Moon causes the ocean levels to rise and fall, creating tidal movements that have dramatically altered coastlines over millions of years. These tides have been instrumental in developing ecosystems, particularly in the intertidal zones where a rich diversity of life thrives. Many species, both plant and animal, have adapted over time to these rhythmic changes, relying on the cycles that the Moon orchestrates. In addition to physical changes, the Moon has also had a cultural impact on humanity. Throughout history, it has inspired myths, stories, and even our calendars. Many ancient civilizations considered the Moon sacred, often associating it with various deities and using its phases to mark time. This connection to the lunar cycle has influenced agricultural practices, religious rituals, and navigation, showing just how intertwined the Moon's rhythms are with human development. Finally, the Moon provides a unique opportunity for scientific exploration. By studying lunar geology, we gain insights into the history of our solar system, including a greater understanding of Earth's own history. The Moon acts as a time capsule containing records that have remained largely unchanged for billions of years. In this way, the Moon is not just a distant rock in the sky, it is a vital partner in the story of Earth's development and the evolution of life upon it. The magnetospheres of planets like Jupiter and Saturn are strikingly unique and complex, distinct from those of Earth and other terrestrial planets. One of the most fascinating aspects is their sheer size. Jupiter possesses the largest magnetosphere in the solar system, extending millions of kilometers into space. This vast region of magnetically influenced space is shaped by the intense magnetic field generated by the planet's rapid rotation and its metallic hydrogen core. In comparison, Saturn's magnetosphere, while smaller than Jupiter's, is still a powerhouse, extending about 1.5 times the distance from the planet to the Sun. Both Jupiter and Saturn's magnetospheres are characterized by their dynamic interactions with the solar wind, the continuous flow of charged particles emitted by the Sun. This interaction creates stunning auroras at the poles of both planets, far more powerful than those seen on Earth. The auroras are driven by the complex dance of charged particles spiraling into the magnetic field lines, resulting in bright glows that can be observed from space. Interestingly, these auroras also vary in intensity, responding to the solar wind's conditions. Another peculiar feature is the presence of numerous moons that significantly influence these magnetospheres. Jupiter, for example, has an array of volcanic moons, like Io, which eject significant amounts of material into space. This volcanic activity contributes to a torus of plasma around Jupiter, intensifying its magnetic field. Saturn's moon Enceladus behaves similarly, releasing jets of water ice that interact with its magnetosphere and produce a complex ring of charged particles, enhancing its already rich plasma environment. The peculiarities of these magnetospheres also extend to their somewhat mysterious particles. Scientists have identified energetic electrons and protons, as well as heavier ions, swirling within these magnetospheric environments. The study of these particles reveals insights into the processes governing planetary atmospheres and space weather. Understanding the intricacies of Jupiter and Saturn's magnetospheres not only sheds light on the nature of these giant planets, but also enhances our comprehension of magnetism and its effects beyond our own Earth. Albert Einstein's theory of general relativity fundamentally transformed our comprehension of time and space, presenting them not as separate and static entities, but as interwoven dimensions within a malleable fabric known as spacetime. Before Einstein, most scientists viewed gravity as a force acting at a distance, but he proposed that what we perceive as gravity is actually the result of massive objects bending the spacetime around them. This insight has profound implications for how we experience time. In this framework, time is not a constant. It varies based on how close an object is to a massive body. For instance, time flows slightly slower near a heavy mass like a planet compared to a location far away from any significant gravitational influence. This phenomenon, known as time dilation, was famously illustrated by the thought experiment of twins. Imagine one twin traveling close to the speed of light, while the other remains on Earth. Upon the traveling twins' return, they will have aged considerably less than their Earth-bound sibling. This counterintuitive concept reveals how interconnected time and space truly are. Moreover, Einstein's theory allows for the possibility of warped spacetime, leading to phenomena such as black holes, regions where gravity is so intense that not even light can escape. These vast voids challenge our understanding, suggesting that escaping their gravitational pull is impossible, which raises questions about the fate of matter and information. The boundaries of black holes, known as event horizons, hint at the limits of our knowledge, where physics as we know it may break down. As we delve deeper into the cosmos, the implications of general relativity are not only theoretical, but also practical. Technologies like GPS rely on this reshaped understanding, requiring adjustments for time dilation due to Earth's gravity to ensure accurate positioning. Einstein's theory has irrevocably changed our perception, showing us that time and space are dynamic, deeply affected by the universe's structure and the objects within it, continuously inviting us to explore further into the mysteries of the cosmos. Quantum mechanics is a branch of physics that explores the behavior of matter and energy at the smallest scales, particularly at the level of atoms and subatomic particles. It reveals a world where the rules of classical physics no longer apply, introducing concepts that seem counterintuitive, such as particles being in multiple states at once, and the peculiar notion of entanglement, where particles become linked despite vast distances. This framework fundamentally changes our understanding of nature, suggesting that the universe operates under principles more complex than our everyday experiences suggest. In astrophysics, quantum mechanics provides crucial insights into phenomena that take place in the high-energy environment beyond our planet. For instance, stars, including our Sun, derive their energy from nuclear fusion, processes that are governed by quantum principles. At the core of these enormous celestial bodies, hydrogen nuclei collide and fuse to form helium, a transition that requires overcoming significant energy barriers. Quantum tunneling, a concept where particles can pass through barriers they seemingly should not surmount, plays a pivotal role in making this fusion occur at the temperatures and pressures present in stars. quantum mechanics is also essential in understanding black holes and the behavior of light in extreme gravitational fields. The interaction between light and matter under these conditions leads to various astrophysical phenomena, such as Hawking radiation, which posits that black holes can emit radiation due to quantum effects near their event horizons. This concept challenges traditional notions of black holes as entirely dark entities and introduces a fascinating link between quantum information and gravitational theory, compelling us to reconsider how matter and energy function in the universe. Furthermore, the intersection of quantum mechanics and astrophysics paves the way for exploring the fundamental nature of reality itself. This includes questions about the fabric of space and time, the origin of the universe during the Big Bang, and theories that unite quantum mechanics with general relativity, such as string theory and loop quantum gravity. As scientists continue to investigate these mysteries, quantum mechanics remains a cornerstone for understanding not just the smallest particles, but the grand tapestry of the cosmos itself. String theory represents a bold attempt to unify the conflicting branches of physics that describe our universe. At its core, string theory posits that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. These strings can oscillate in different ways, and it is through their vibrations that particles manifest, each corresponding to a specific vibrational pattern. This elegant framework offers a potential theory of everything, aiming to unify general relativity, which describes gravity, with quantum mechanics, which governs the behavior of particles at the smallest scales. One of the striking aspects of string theory is its requirement for additional dimensions beyond the four we commonly experience: 3 dimensions of space and 1 of time. In the simplest models, string theory suggests there could be as many as 10 or 11 dimensions. These extra dimensions are theorized to be compact and curled up in ways that make them imperceptible in our everyday experiences. By incorporating these hidden dimensions, string theory provides a platform to reconcile the fundamental forces of nature, including gravity, electromagnetism, and the strong and weak nuclear forces. However, string theory is not without its challenges, particularly in terms of experimental verification. Unlike previous theories that could be tested or observed directly, the scales at which string theory operates are far beyond current experimental capabilities. This has led to debates within the scientific community regarding its status as a theory. While it has garnered significant mathematical support, the lack of empirical evidence raises questions about its scientific validity, forming a barrier to its acceptance. Despite these hurdles, string theory inspires a vast amount of research and speculation. Scientists continue to explore its implications and potential outcomes, not only for theoretical coherence, but also for practical applications. By pushing the boundaries of our understanding, string theory invites intriguing possibilities, inviting us to contemplate the very nature of reality itself in our quest to uncover the mysteries of the universe. The multiverse theory is a concept in cosmology that suggests the existence of multiple, possibly infinite, universes beyond our own. These universes could have different physical laws, constants, and even dimensions. Imagine a vast cosmic landscape where every conceivable outcome of every event spawns a new universe. That is the essence of the multiverse. It challenges our understanding of reality, suggesting that what we perceive as the entire universe might just be a tiny fraction of a much larger and complex web of parallel worlds. One of the main hypotheses supporting the multiverse theory comes from inflationary cosmology. In simple terms, inflation refers to a period shortly after the Big Bang when the universe expanded rapidly. Some models propose that this inflationary process did not occur uniformly throughout space. Instead, it was patchy, creating bubbles or regions, each evolving into its own universe with distinct properties. This means that while our universe is one bubble in a vast sea, other bubbles exist with entirely different characteristics, leading to a diverse tapestry of universes. Another support for this theory is found in quantum mechanics, particularly the concept of superposition. When particles exist in a state of superposition, they can exist in multiple states at once, and only when observed do they collapse into a single outcome. The many worlds interpretation of quantum mechanics suggests that all possible outcomes happen in separate, branching universes. This may imply that every event in our universe spawns a parallel reality where different outcomes play out simultaneously. While direct evidence for the multiverse remains elusive, the implications of string theory further bolster the idea. String theory attempts to unify the fundamental forces of nature and posits additional dimensions beyond our familiar space and time. In this complex framework, the multiverse emerges as a natural outcome, suggesting that many different physical realities can exist based on the arrangement of these extra dimensions. As scientists continue to explore these theories, the multiverse remains one of the most fascinating and mind-bending possibilities in understanding our cosmos. Wormholes, often described as shortcuts through the fabric of spacetime, emerge from the equations of general relativity proposed by Albert Einstein. Picture spacetime as a two-dimensional sheet of rubber. If you could bend the sheet and create a tunnel connecting two distant points, you would have a visual representation of a wormhole. While this intriguing idea has captured the imagination of scientists and sci-fi enthusiasts alike, it remains theoretical, resting on complex mathematics and concepts we have yet to fully comprehend in practice. In theory, wormholes could function as portals, allowing for rapid travel between galaxies or even between different points in time. If we could stabilize a wormhole, it might enable a spaceship to traverse vast distances in a fraction of the time it would take using conventional means. Imagine setting off from our solar system and arriving at a distant galaxy in mere moments rather than millions of years. This exciting concept has fueled countless stories and hypotheses about interstellar travel, challenging our understanding of physics and the universe. However, several significant hurdles exist on the path to realizing wormholes. First, they would likely require an enormous amount of negative energy to keep them open, a substance that, as of now, remains hypothetical. Furthermore, the geometry of a wormhole might be unstable, potentially collapsing before any traveler could pass through. Even if we could construct a wormhole, the dangerous gravitational forces near the entrance could pose deadly threats to potential travelers. Despite these challenges, the theoretical exploration of wormholes pushes the boundaries of our understanding of the cosmos. They inspire a sense of wonder about the universe's possibilities and the nature of space-time itself. While practical use remains within the realm of speculation, continued research into the properties of wormholes may one day reveal groundbreaking insights into how we perceive distance and travel across the vast expanses of the universe. Time dilation is a fascinating concept arising from the theory of relativity, and it has profound implications for space travel. As we venture into the cosmos, we must grapple with the fact that time does not pass uniformly for all observers. It depends heavily on one's relative speed and the strength of gravitational fields. For astronauts traveling at speeds close to the speed of light, time will slow down for them compared to people remaining on Earth. This means that while they may experience only a short journey, years could pass back home. One of the more intriguing scenarios involves space travel to distant star systems. Let's say a spacecraft were to journey to a star several light years away at significant fractions of light speed. Due to time dilation, the crew might age only a couple of years during their trip, while many years or even decades could pass on Earth. This discrepancy creates profound challenges for mission planning and the potential return to a planet that has aged significantly since their departure. Additionally, this phenomenon isn't just a hypothetical concept. It has been confirmed through experiments involving atomic clocks on fast-moving jets, where clocks on board registered less time than those on the ground. This difference, however small, provides concrete evidence of time dilation in action. As humanity considers interstellar travel or colonization of other planets, it raises questions about how space travelers will adapt to a different time frame upon their return. Understanding time dilation also pushes the boundaries of our communication methods across vast distances. Signals sent back to Earth would also experience delays, compounding the feeling of disconnection between astronauts and their home planet. As we continue exploring the universe, embracing these implications of time becomes not only a scientific curiosity, but a necessary piece of our journey into the great unknown. The quest to understand how life might emerge on other planets is one of the most profound questions in both astrobiology and cosmology. Scientists have proposed several leading theories that explore the origins of life beyond Earth. One prominent theory is the idea of abiogenesis, which suggests that life can arise naturally from non-living matter. This process likely involves simple organic compounds, which could gradually combine to form more complex molecules like amino acids and eventually lead to cellular life. These reactions might occur in environments rich in energy, such as hydrothermal vents on ocean floors or the shallow pools on early Earth. Another intriguing possibility involves panspermia, the hypothesis that life did not originate on Earth at all, but rather was brought here by comets, meteorites, or cosmic dust. This theory posits that microbial life, or at least the building blocks for life, could survive the harsh conditions of space travel. Recent discoveries of extremophiles, organisms that thrive in extreme environments, bolster this idea, suggesting that life might endure the conditions of space and potentially colonize other worlds. Moreover, researchers consider alternative biochemistries that could exist in environments radically different from our own. For instance, while life on Earth depends on carbon and water, some theorists speculate about silicon-based life forms or those that might utilize solvents other than water. The discovery of exoplanets in their stars' habitable zones has spurred imagination and rigorous scientific inquiry into how diverse potential life might be out there. Finally, the study of extreme environments on Earth continues to fuel our understanding of life's adaptability. From the icy realms of Antarctica to the sulfur-rich pools of Yellowstone, life has shown a remarkable ability to thrive where conditions seem inhospitable. This adaptability raises the possibility that similar conditions elsewhere in the universe could also harbor life forms, expanding our perspectives on what constitutes a livable environment. The search for extraterrestrial life continues, blending curiosity with scientific inquiry and inching us closer to answering the monumental question of whether we are alone in the cosmos. Scientists are employing a variety of innovative methods to search for signs of extraterrestrial life within our solar system. Their efforts span across multiple planets, moons, and even asteroids, focusing on environments that could potentially harbor life. These explorations are driven by the understanding that life, as we know it, requires water, energy, and organic compounds. One of the most promising targets in this quest is Mars. Robotic missions, like the Perseverance rover, are conducting a thorough analysis of the Martian surface and its geology. These rovers not only search for signs of ancient microbial life, but also collect soil samples that may one day be returned to Earth for more detailed study. Scientists are particularly interested in areas where water once flowed, as these environments are more likely to hold biological traces. Beyond Mars, researchers are turning their attention to the icy moons of Jupiter and Saturn. Europa, a moon of Jupiter, is believed to have a vast ocean beneath its frozen crust, which could provide the necessary conditions for life. Similarly, Enceladus, Saturn's moon, has geysers that eject plumes of water vapor and organic molecules into space. Future missions are planned to directly sample these plumes, allowing scientists to analyze the chemical composition and search for biological indicators. The hunt for extraterrestrial life also extends to comets and asteroids, which could contain the building blocks of life or evidence of past life. By studying these celestial bodies, scientists hope to gather insights into how life may have originated and whether it could exist beyond Earth. The search is not just about finding life, it's about understanding the conditions that support it, ultimately offering a broader perspective on the universe and our place within it. When we ponder the quest for life beyond our planet, certain celestial bodies draw our attention due to their unique environments. One of the most intriguing locations is Mars. This red planet has long fascinated scientists because of evidence that suggests it once had a warmer, wetter climate. Features such as ancient river valleys, lake beds, and polar ice caps hint at a time when liquid water flowed freely. Ongoing missions continue to explore its surface in the hopes of uncovering microbial life or remnants of past life. Another exciting prospect lies with the moons of Jupiter and Saturn. Europa, one of Jupiter's moons, is believed to have a vast ocean beneath its icy crust. This subsurface ocean, kept warm by the moon's gravitational pull, raises the possibility that conditions there could be suitable for life. Similarly, Enceladus, a moon of Saturn, has shown evidence of water geysers that spew plumes of ice and organic compounds into space. The potential for these environments to host microbial life has made them prime targets for future exploration. Beyond our solar system, exoplanets, planets orbiting other stars, are setting the stage for new discoveries. The habitable zone, often termed the Goldilocks zone, is where conditions might be just right for liquid water to exist. Planets like Proxima Centauri b, located in the habitable zone of our closest star, have sparked immense interest. Scientists are using advanced telescopes to detect the atmospheres of these distant worlds, searching for biosignatures like oxygen or methane that could indicate the presence of life. Astrobiology, the study of life in the universe, continues to evolve with every mission and discovery. Each new finding from Mars, the icy moons of our solar system, or distant exoplanets adds another piece to the cosmic puzzle. As technology improves and our understanding deepens, the potential for discovering life beyond Earth feels more tangible than ever, igniting our curiosity and wonder about the universe. The search for extraterrestrial intelligence, often abbreviated as SETI, operates through a series of well-planned initiatives aimed at detecting signals from other civilizations beyond our planet. Scientists involved in SETI utilize a wide array of radio telescopes to scan the cosmos for electromagnetic signals that stand out among the overwhelming noise of the universe. The basic idea is simple. If intelligent life exists elsewhere, it may be sending messages into space, and we just need to listen. Radio frequencies have been the primary focus of SETI because they can travel vast distances without significant interference. One of the most well-known SETI programs uses large, powerful dishes to surveil specific stars that exhibit characteristics suggesting they might harbor planets. By collecting and analyzing data from these signals, scientists are on the lookout for patterns or structures that could indicate an artificial origin, distinguishing them from natural cosmic phenomena. In recent years, technology has advanced significantly, allowing for more sophisticated techniques in data analysis. For instance, machine learning algorithms can process vast amounts of data in real time, enabling scientists to identify potential signals much faster than before. Additionally, researchers are developing optical SETI programs that search for laser communications rather than traditional radio waves, expanding the scope of their quest. Public collaboration also plays a role in SETI efforts, with initiatives like SETI Home inviting citizen scientists to contribute their computer power to analyze signals from radio telescopes. This democratization of scientific inquiry not only accelerates research, but stirs public interest in the search for extraterrestrial life. As we look at the stars, SETI represents our collective endeavor to listen for the echoes of other intelligent beings across the universe, inviting us to ponder our place in the cosmic narrative. Communicating with potential extraterrestrial civilizations is a fascinating yet deeply complex challenge. One of the foremost issues is simply finding common ground in terms of language and meaning. If we assume intelligent extraterrestrial life exists, it's likely that their communication methods and even the very concepts they understand are vastly different from ours. We rely on spoken languages, symbols, and physical gestures, but alien civilizations might utilize methods beyond our current comprehension, perhaps even forms of communication we don't recognize as language at all. Distance also presents a significant hurdle in establishing contact. The vastness of space means that signals sent from Earth take considerable time to reach other star systems. For instance, if we send a message to a planet located 10 light-years away, it takes 10 years for our signal to arrive, and then the same amount of time for a reply to reach us. This means the timeline for communication could span decades, hundreds of years, or even longer, making it difficult to establish a meaningful dialogue. Each transmission could feel like a solitary echo in the cosmos, filled with uncertainty about whether anyone is listening or capable of responding. Another challenge is the signal itself. Current efforts to communicate, whether through radio waves or other means, may not be detectable by extraterrestrial civilizations. Our signals might be too weak, lost in the background noise of cosmic events, or simply not understood by civilizations that have evolved entirely different technologies. Additionally, the potential for messages to degrade over astronomical distances is a real concern. Ensuring that our communications withstand the passage of time and distance is crucial for effective outreach. Lastly, there's the question of intent and perception. How might an alien civilization interpret our messages? What if they misinterpret our attempts at connection as threats rather than invitations? The possible cultural misalignments could result in scenarios we cannot predict, leading to profound implications for interstellar diplomacy. Establishing a reliable and meaningful exchange across such differences is a challenge that both our technology and our understanding of life beyond Earth will need to overcome in this ongoing quest for connection among the stars. Astrobiology, the study of life in the universe, explores the conditions that allow life to thrive beyond Earth. A crucial aspect of this field is the examination of extremophiles, organisms that survive in environments previously thought to be hostile to life. These remarkable creatures have transformed our understanding of resilience and adaptability. By studying extremophiles, researchers can uncover the potential for life to exist in myriad environments, from the icy moons of our solar system to distant exoplanets. Extremophiles come in various forms, exhibiting extraordinary capabilities to endure extreme heat, acidity, salinity, and pressure. For instance, certain bacteria thrive in boiling hot springs, while others can survive the frigid conditions of Antarctica. Some even flourish in highly acidic lakes or deep-sea hydrothermal vents. These adaptations not only challenge our definitions of life, but also suggest that the fundamental biochemistry of life is more versatile than previously assumed. The existence of extremophiles raises exciting possibilities for life beyond Earth, particularly in places where conditions are extreme. Scientists are now focusing on celestial bodies like Europa, one of Jupiter's moons, which is believed to have a subsurface ocean beneath its icy crust. If life can endure on Earth in such severe habitats, it is plausible that similar organisms may exist in these unlikely environments, expanding the realms of where we might find life. Moreover, studying extremophiles could impact our approach to astrobiology and the search for extraterrestrial life. Their unique survival strategies inspire innovative techniques to detect life. By understanding how these organisms thrive against extreme odds, we can better prepare for missions aimed at discovering life on other planets, helping us redefine where and how we look. The quest to find life beyond our home planet becomes not only a journey through space, but a profound exploration of the resilience of life itself. Space telescopes, beginning with the Hubble Space Telescope, have dramatically transformed our understanding of the cosmos. Launched in 1990, Hubble provided astronomers with a clear, unobstructed view of the universe, free from the distortion and interference caused by Earth's atmosphere. This capability has allowed Hubble to capture breathtaking images of distant galaxies, nebulae, and other celestial phenomena, which were previously hidden from ground-based observatories. One of the most significant impacts of Hubble has been its role in helping to measure the rate of expansion of the universe. By analyzing the light from faraway galaxies, astronomers discovered that the universe is not only expanding, but that this expansion is accelerating. This revelation pointed towards the existence of dark energy, a mysterious force that constitutes much of the universe but remains largely unexplained. Such findings have reshaped our theories about the universe's past, present, and future. Hubble has also contributed to our understanding of galaxy formation and evolution. By observing galaxies at different stages of development, scientists have pieced together a timeline of how galaxies evolve over billions of years. This research has illuminated the complex interactions between galaxies, such as mergers and collisions, allowing us to better understand our own Milky Way's history in the grand cosmic dance. Beyond just providing stunning images, space telescopes like Hubble have become essential tools for scientific discovery. They have turned the cosmos into a vast laboratory, allowing researchers to explore the fundamental laws of physics, the life cycle of stars, and the conditions necessary for life. With every new observation, our perception of the cosmos expands, revealing a universe more intricate and fascinating than ever imagined. The James Webb Space Telescope, often referred to as Webb, represents a significant leap forward in our quest to understand the universe. Launched with the primary goal of observing the cosmos in infrared light, Webb can peer through dust clouds that often obscure our view of celestial objects. This capability will allow astronomers to study the formation of stars and planetary systems, shedding light on the processes that shaped our own solar system. One of the most exciting advancements anticipated from Webb's mission is the investigation of exoplanets, or planets outside our solar system. Webb's powerful instruments will enable scientists to analyze the atmospheres of these distant worlds, searching for essential elements like water vapor, carbon dioxide, and even conditions that might be suitable for life. By providing unprecedented details about these planets, Webb is poised to answer fundamental questions about the prevalence of life beyond Earth. Furthermore, Webb is designed to look back in time, observing the first galaxies that formed after the Big Bang. By analyzing these ancient galaxies, researchers hope to understand how the universe evolved from a hot, dense state to the vast, complex cosmos we observe today. This could revolutionize our understanding of cosmic history and the fundamental forces that govern the universe. In addition to its scientific objectives, Webb's advancements will have broader implications for technology and engineering. The innovations developed for this mission could spill over into other fields, fostering advancements in optics, materials science, and data analysis. With its capability to answer some of humanity's most profound questions, the James Webb Space Telescope is more than just a scientific instrument. It's a monumental step in our exploration of the universe. Robotic missions have revolutionized our understanding of planets and moons in ways that human explorers could only dream of achieving within the same time frame. These advanced machines are designed to travel vast distances, navigate hostile environments, and carry out an array of scientific tasks, all without the limitations that human beings face. As a result, they can operate in extreme conditions, from the scorching heat of Venus to the frigid surfaces of the moons of Jupiter and Saturn. This adaptability allows scientists to gather data from places that would be otherwise unreachable for humans. One of the most significant advantages of robotic missions is their ability to remain in space for extended periods, analyzing and collecting data continuously. With no need for life support systems or considerations for human safety, spacecraft can be built to endure long journeys. They can gather information over years, sending back vital insights about atmospheric conditions, geology, and potential for life. For example, the Mars rovers have provided us with a treasure trove of information about the planet's surface, including evidence of past water flows that significantly reshaped our understanding of its history. Moreover, robotic missions can be equipped with cutting-edge technology that enhances their observational capabilities. From sophisticated cameras and spectrometers to powerful drills and landers, these tools allow the missions to analyze soil samples, capture detailed images, and study radiation levels. This technology facilitates the discovery of not just basic data, but also complex phenomena, such as the detection of organic molecules or the mapping of ice deposits on other celestial bodies, which offer clues to the potential for life beyond Earth. Finally, the data returned from robotic missions has had a profound impact on scientific theories and our exploration strategies. It informs future missions, guiding where we should send humankind next and what areas warrant further investigation. Robotic missions serve as our eyes and ears in the far reaches of our solar system, providing invaluable insights that expand our knowledge and fuel our curiosity about the cosmos. Since the dawn of space exploration, rovers have unlocked an astonishing treasure trove of information about our neighboring planet, Mars. The first successful rover, Sojourner, landed on Mars in 1997, paving the way for a series of ingenious robotic explorers. These rovers have been instrumental in examining the Martian surface, analyzing soil and rock samples, and capturing images of diverse geological formations. Notably, the Spirit and Opportunity rovers made groundbreaking discoveries by revealing evidence of past water flow, showcasing that liquid water once existed on Mars, significantly shaping our understanding of its potential to host life. In more recent years, the Curiosity rover, which landed in 2012, has delved deeper into the Martian terrain and atmosphere. This car-sized robot has discovered organic molecules and seasonal methane fluctuations, hinting at Mars's past conditions that may have been favorable for life. Curiosity has also been exploring the Gale crater, studying sedimentary rocks that offer clues about the planet's watery past, therefore deepening our insights into the evolution of its climate and geology. The most current rover, Perseverance, landed on Mars in February 2021 and is tasked with even more ambitious goals. Equipped with advanced scientific instruments, it is exploring the Jezero crater, believed to be an ancient lakebed. One of its primary objectives is to search for signs of past microbial life by not only examining rock and soil samples, but also collecting and storing those samples for future analysis. Additionally, Perseverance is experimenting with producing oxygen from the Martian atmosphere, an essential step for future human missions. As for the future, numerous missions are in the works. NASA's Artemis program aims to return humans to the Moon and eventually embarks on a route to Mars, with plans for a crewed mission taking shape. The European Space Agency and NASA are collaborating on the Mars Sample Return mission, which aims to bring the samples collected by Perseverance back to Earth. This synergy of exploration, both robotic and human, promises to deepen our understanding of Mars and possibly unlock answers about the existence of life beyond our planet. The story of Mars continues to unfold, and with every rover mission, we inch closer to uncovering the planet's long-held secrets. International collaboration is a cornerstone of modern space exploration, driving advancements beyond what any single nation could achieve alone. By pooling resources, expertise, and technologies, countries can embark on ambitious projects that push the boundaries of human knowledge and capability. For instance, the International Space Station, a joint effort involving multiple nations, serves as a platform for research, international diplomacy, and technological innovation. This facility symbolizes the power of collaboration, allowing scientists from diverse backgrounds to work together on experiments that benefit humanity as a whole. Working together in space exploration also fosters the sharing of ideas and best practices. Different countries bring unique perspectives and approaches to problem solving, which can lead to creative solutions that might not emerge in isolation. For instance, the diverse design philosophies of spacecraft and instruments can be combined to enhance performance and efficiency. Furthermore, by collaborating, nations are able to distribute costs more evenly, making large-scale missions more financially viable. This not only reduces economic burden, but also accelerates the pace of innovation. Moreover, international cooperation in space can help maintain peace and stability on Earth. When nations collaborate in the pursuit of common goals, such as exploring Mars or studying climate change from above, they foster goodwill and understanding. This unity offers an avenue for diplomacy that transcends national borders, demonstrating the benefits of collaboration over competition. Initiatives that involve gathering data from space also lead to significant advancements in monitoring Earth's environment, which is crucial for addressing global challenges like climate change and natural disasters. Finally, international collaboration encourages the development of a new generation of scientists and engineers. Programs that allow students and young professionals to interact with their peers globally nurture a shared sense of purpose and curiosity. This environment of cooperation not only inspires the next generation, but also ensures that the field of space exploration is enriched with diverse voices and ideas. The continued expansion of international partnerships promises to unlock even more exciting discoveries in the universe we inhabit. As we stand on the brink of a new era in space travel technology, some extraordinary advancements are reshaping our approach to exploration. From reusable rocket systems to advanced propulsion methods, these innovations promise to redefine not only how we reach further into the cosmos, but also how we perceive our place within it. Among the most groundbreaking advancements is the development of reusable launch vehicles. Companies like SpaceX have showcased the viability of landing rocket boosters back on Earth after launching, significantly slashing costs and making space travel more sustainable. Another exciting frontier is the emergence of ion propulsion and other electric propulsion technologies. Unlike traditional chemical rockets, which burn fuel to create thrust, ion drives utilize electricity to accelerate ions, providing continuous thrust over long periods. This method allows for more efficient exploration of distant destinations, potentially cutting travel time to Mars and beyond. As we enhance our propulsion capabilities, the expansiveness of the universe feels increasingly reachable, opening doors to numerous celestial bodies that were once thought to be out of our reach. Human exploration is also on the cusp of transformation with the potential colonization of other planets. Here, technologies such as 3D printing and closed-loop life support systems come into play. They promise to create self-sustaining habitats that could support human life far from Earth. Imagine building structures on Mars using local materials or recycling every element of waste to ensure sustainability. This would revolutionize our approach to long-duration missions and could enable extended stays on other planets, fostering more profound research and insights. Moreover, the integration of artificial intelligence and robotics into space exploration will vastly enhance our capabilities. Autonomous spacecraft and rovers can explore terrains and perform tasks that would be hazardous for human astronauts. This synergy between human ingenuity and machine efficiency is likely to expand our understanding of the universe while mitigating the risks associated with human spaceflight. As we progressively push the boundaries of our technology, we stand at the threshold of a golden age of exploration, one that will not only propel us to new worlds, but also redefine what it means to be human in the cosmos. Gamma-ray bursts are incredibly powerful explosions observed in distant galaxies, producing the brightest flashes of gamma rays known to humanity. These bursts are so intense that they can outshine entire galaxies for a brief period, typically lasting from a few milliseconds to a few minutes. They are believed to occur during cataclysmic events like the collapse of massive stars into black holes or the merging of neutron stars. As these events unfold, they release enormous amounts of energy in the form of gamma rays, creating a cosmic spectacle that captivates astronomers. The study of gamma-ray bursts fascinates astronomers for several reasons. First, they represent the most energetic events in the universe. Understanding their mechanisms not only illuminates the extremes of our universe's physics, but also provides a glimpse into the life cycles of stars and the processes involved in black hole formation. By analyzing the light and energy released from these bursts, scientists can infer details about the nature of these celestial bodies and environments. Moreover, gamma-ray bursts serve as cosmic markers, helping astronomers probe the structure and evolution of the universe itself. The light from these bursts can travel billions of years to reach Earth, allowing researchers to study ancient galaxies and the conditions that existed when the universe was young. This offers valuable insights into the formation of stars and galaxies, making them crucial to our understanding of cosmology. Finally, the potential for discovering new physics also draws researchers to gamma-ray bursts. They challenge existing theories and prompt new questions about fundamental forces and materials in the universe. Each discovery related to these cosmic events opens the door to deeper understanding and propels us toward uncovering more of the universe's mysteries. It's a field filled with wonder, as each burst has the potential to unveil secrets hidden in the fabric of space-time itself. Quasars and pulsars are two extraordinary cosmic phenomena that push the boundaries of our astrophysical knowledge and understanding of the universe. Quasars, or quasi-stellar objects, were first discovered in the 1960s as extremely bright, distant objects. They emit enormous amounts of energy, outshining entire galaxies. What makes quasars truly fascinating is their power source, a supermassive black hole at the center of a distant galaxy, surrounded by an accretion disk of gas and dust. This disk accelerates and heats to such extreme temperatures that it emits intense radiation, making quasars some of the brightest objects observable in the universe. Pulsars, on the other hand, are highly magnetized, rotating neutron stars that emit beams of electromagnetic radiation. When these beams are pointed toward Earth, they appear to pulse with remarkable precision, similar to a lighthouse beacon. Discovered in the late 1960s, pulsars initially puzzled scientists. Their consistent and rapid rotation challenges our understanding of stellar evolution and the behavior of matter in extreme conditions. These tiny remnants of massive stars, typically just a few kilometers in diameter, possess incredibly dense cores, with a mass greater than that of the Sun compressed into a minuscule volume. Both quasars and pulsars compel astrophysicists to rethink existing theories about the universe. The study of quasars helps astronomers probe the properties of black holes and the evolution of galaxies across cosmic time. They act as beacons, guiding us to understand the formation of structures in the universe and the nature of dark energy and dark matter. The extreme conditions under which pulsars exist offer insights into the fundamental forces of nature, including gravity, electromagnetism, and nuclear forces at play in neutron stars. These phenomena continuously raise questions about our models of the cosmos, prompting new inquiries into the fundamental laws governing the universe. As we explore these celestial wonders further, quasars and pulsars invite us to expand our understanding of astrophysics and the intricate tapestry of existence in the vast universe beyond our planet. Fast radio bursts, often abbreviated as FRBs, are powerful and brief bursts of radio waves that last just a few milliseconds. First discovered in 2007, these enigmatic signals originate from galaxies far beyond our own Milky Way. What makes them particularly fascinating is their tremendous energy, which can surpass that of hundreds of millions of suns concentrated in an instant. Despite their brief duration, their brightness allows them to be detected over billions of light years, making them both a scientific mystery and a source of wonder. The origins of these radio bursts are still largely unknown. Scientists have proposed various theories, ranging from pulsars, rapidly rotating neutron stars emitting beams of radiation, to more exotic possibilities, like black hole mergers, or even advanced extraterrestrial communication. Each of these potential sources raises significant questions about the nature of the universe. Are we witnessing the aftermath of cataclysmic cosmic events, or are we perhaps receiving messages from intelligent life far beyond our solar system? Moreover, fast radio bursts also prompt inquiries into the structure of the universe itself. As these signals travel across the cosmos, they interact with the matter and radiation they encounter. This interaction provides astronomers with valuable information about the intergalactic medium, the space between galaxies, and the distribution of matter throughout the universe. Analyzing FRBs can thus help scientists refine their understanding of cosmic evolution and the large-scale structure of the universe. Fast radio bursts are not just signals, they are clues to some of the most profound mysteries of the cosmos. Each burst invites us to explore and question the fundamental workings of the universe, challenging our understanding of everything from the birth of stars to the potential existence of life beyond Earth. As researchers continue to study these intriguing phenomena using advanced technology and collaboration across the globe, the universe may still have many surprises in store. Gravitational waves are ripples in spacetime produced by some of the universe's most massive and dynamic events. They were first predicted by Albert Einstein over a century ago as a part of his theory of general relativity. But it wasn't until 2015 that the Laser Interferometer Gravitational Wave Observatory, or LIGO, finally detected these elusive waves. This groundbreaking discovery opened a new window into observing the cosmos by allowing scientists to listen to the movements of celestial bodies in a way that is utterly distinct from traditional electromagnetic observations, such as light. When massive objects like black holes or neutron stars collide, they create gravitational waves that travel across the universe at the speed of light. The unique properties of these waves carry information about their origins and the physical characteristics of the source. For instance, the frequency and amplitude of the waves can indicate the mass of the objects involved and the speed at which they were moving before colliding. This means that by analyzing the waves, scientists can glean insights into events that have taken place billions of light years away, from the merging of black holes to the explosive death of stars. What makes gravitational waves particularly compelling is their ability to provide data on events that are otherwise hidden from optical telescopes. For example, colliding black holes can merge without emitting any light at all, rendering them invisible to conventional methods of observation. Gravitational waves give us access to these hidden cosmic phenomena, enriching our understanding of the universe and confirming predictions made by general relativity. They allow for a multi-messenger approach to astronomy, where information can be gathered from both electromagnetic radiation and gravitational waves, leading to more comprehensive insights about the workings of the universe. As the technology continues to advance, scientists anticipate detecting more gravitational waves from a wider array of cosmic events. This exploration may ultimately reveal new information about the formation and evolution of galaxies, the nature of dark matter, and the fundamental laws of physics that govern our universe. These discoveries hold the potential to reshape our understanding of not only celestial dynamics, but also the very structures that form the fabric of space-time itself. The transit method of exoplanet detection has revolutionized our understanding of distant worlds in ways that were once unimaginable. This technique involves monitoring the light from a star for periodic dips in brightness caused when a planet passes in front of it. By analyzing these transits, astronomers can infer a planet's size, orbital period, and distance from its star. This method has allowed us to compile an impressive catalogue of thousands of exoplanets, revealing a vast and diverse array of planetary systems beyond our own. Before the advent of the transit method, most of what we knew about planets outside our solar system was based on indirect measurements. The discovery of exoplanets relied heavily on techniques that were less reliable and often limited to detecting large, gas-giant planets similar to Jupiter. However, with the transit method, astronomers can now find smaller, Earth-sized planets that reside in the so-called habitable zone, the region where conditions might be right for liquid water to exist. This has opened a new chapter in our search for potentially habitable worlds. Moreover, the data collected through transit observations allow astronomers to study the atmospheric compositions of these distant planets. By observing the starlight that filters through a planet's atmosphere during transit, scientists can identify various gases, such as water vapor, carbon dioxide, and methane. This groundbreaking capability has given us insights into the potential for life on these exoplanets, as certain atmospheric characteristics could suggest the presence of biological processes. The transit method has not only expanded our knowledge about the existence of exoplanets, but has also deepened our understanding of their potential habitability. It provides a window into a universe teeming with possibilities, inviting us to ponder the richness and diversity of planetary systems that exist beyond our own. Each new discovery brings us closer to answering one of humanity's most profound questions. Are we alone in the universe? Throughout the history of science, researchers have encountered a number of unexplained anomalies that challenge our current understanding of the universe. One of the most puzzling examples is dark matter, Despite comprising about 26% of the universe, it remains invisible and undetectable through traditional means. We know dark matter exists because of its gravitational effects on galaxies and cosmic structures, yet we have yet to identify what it is or how it interacts with ordinary matter. Another enigma is dark energy, an even more mysterious force driving the accelerated expansion of the universe. Thought to make up around 70% of the universe, dark energy defies our fundamental understanding of how gravity should behave. Scientists realize that despite its overwhelming presence, our grasp of dark energy and its properties is still insufficient, leaving researchers grappling with the implications it has for the fate of the cosmos. Quantum mechanics introduces further mysteries with phenomena like quantum entanglement. This strange occurrence reveals that particles can become interconnected in ways that seem to defy the constraints of distance. When one particle changes, its entangled partner reflects that change instantly, no matter how far apart they are. Such behavior challenges our understanding of space and time, suggesting that the fabric of reality might be woven together in ways we have yet to comprehend fully. Additionally, observational evidence of fast radio bursts has taken the astronomy world by surprise. These brief, high-energy flashes of radio waves come from unknown locations in the universe, and their origins are still a topic of heated debate. Proposals for their sources range from exotic astrophysical phenomena to even more unconventional theories involving advanced extraterrestrial technologies. Each of these anomalies highlights both the progress and the limits of our scientific endeavors, reminding us that the universe still holds secrets waiting to be uncovered. Space colonization, or the idea of humans living permanently beyond Earth, has moved from the realm of science fiction to serious scientific and engineering discussions. With the growing interest in exploring other celestial bodies, especially Mars and the Moon, steps are being taken to make this extraordinary vision a reality. The potential for colonization rests on the advancement of technologies that allow us not only to reach these destinations, but also to sustain human life there over the long term. One of the primary hurdles we face is the development of reliable transportation systems. Sending humans to Mars or the Moon will require spacecraft that can make long journeys with life support capabilities for months at a time. Spacecraft designs need to improve in reliability and safety to ensure the well-being of astronauts during these extended missions. Additionally, the cost of such missions remains a significant barrier. While advancements in reusable rocket technology have reduced costs, funding remains a crucial factor that relies on both governmental space agencies and private enterprises. Once we arrive at a target location, we encounter the challenge of creating habitats that can support life in hostile environments. For instance, Mars has an atmosphere that is mostly carbon dioxide, and surface temperatures can plummet drastically. Colonies will need sustainable systems for producing food, water, and oxygen. Researchers are exploring innovative methods such as growing crops in controlled environments and utilizing resources available on these celestial bodies, a concept known as in situ resource utilization. This approach would allow colonists to rely less on supplies sent from Earth. There are also socio-political and psychological aspects to consider. Establishing a community in space must take into account governance, laws, and social structures, which are uncharted territories in this context. We must ensure that individuals can adapt to living in isolation, far from Earth, and effectively work together in close quarters. Overcoming these multifaceted challenges will be essential for ensuring that space colonization remains not merely a dream, but a tangible, human undertaking. In recent years, the prospect of mining resources from asteroids and other celestial bodies has shifted from science fiction into the realm of serious scientific and economic discussions. With an estimated $10 quintillion worth of resources floating within our solar system, the potential is vast. Asteroids, in particular, are believed to contain valuable metals like platinum, gold, and rare earth elements. These materials could not only support space missions, but also have significant applications on Earth. Organizations and private companies are developing plans to explore and eventually extract these resources. For instance, NASA has been pioneering missions focused on near-Earth asteroids. Their OSIRIS-REx mission, which successfully collected samples from the asteroid Bennu, is a key example of the agency's ambitions in this field. The collected samples will help scientists understand the composition and history of asteroids, paving the way for future mining efforts. Moreover, companies like Planetary Resources and Deep Space Industries have emerged with visions to tap into these celestial riches. They aim to create a new space economy by developing the necessary technology to locate, mine, and transport resources from asteroids back to Earth, or use them to support activities in space. Their plans include prospecting missions, which would identify which asteroids are most resource-rich and suitable for future mining operations. The implications of asteroid mining extend beyond simple resource extraction. By using materials found in space, we could reduce the dependency on mining on Earth, thereby lessening the environmental impact associated with terrestrial mining. This endeavor not only offers the potential to revolutionize our economy, but could also create a sustainable future for space exploration, propelling humanity into a new era of cosmic resource utilization. Space tourism, once a concept confined to science fiction, is poised on the brink of transformation. With companies like SpaceX, Blue Origin, and Virgin Galactic already conducting suborbital flights, we are witnessing the dawn of a new era where ordinary citizens can experience weightlessness and gaze upon Earth from nearly 200 miles above. As technology advances and costs decrease, the experience of traveling into space will likely become more accessible to a broader audience. As space tourism evolves, it could give rise to a multi-billion-dollar industry. Future developments might include longer stays in orbit or even trips to the moon and beyond. Imagine a world where hotel chains cater to guests in low Earth orbit, offering stunning views of the planet while providing a unique vacation experience. These ventures could generate economic growth, creating jobs not only in the aerospace sector, but also in hospitality, transportation, and other ancillary industries. The implications of space tourism extend beyond economics. As more people experience the profound beauty and fragility of our planet from space, there is potential for a shift in perspective regarding environmental issues. Travelers might return home more motivated to advocate for planet preservation and sustainability, having witnessed Earth's vastness and its delicate atmosphere. This could foster a culture of stewardship, inspiring a collective effort towards addressing climate change and resource conservation. Furthermore, the evolution of space tourism may inspire the next generation of scientists, engineers, and explorers. As our society becomes more familiar with the concept of space travel, we could see a surge in interest in STEM fields, as young minds dream of building the next spacecraft or devising new technologies for life beyond Earth. In this way, space tourism could serve as both an adventure and a calling, igniting a curiosity that pushes the boundaries of human achievement in the cosmos. As humanity ignites its ambitions for space exploration, a number of ethical considerations come into play regarding how we interact with other celestial bodies and potential extraterrestrial life. Foremost among these concerns is the preservation of the environments we explore. Many argue that when we venture to planets like Mars or moons such as Europa, we carry the responsibility to protect these locations from contamination. This ongoing conversation urges space agencies to develop strict protocols to prevent Earth microbes from interfering with potential alien ecosystems. An equally significant factor involves the search for extraterrestrial intelligence. The question of whether we should make our presence known to other civilizations, should they exist, remains deeply contentious. Some scientists advocate for a cautious approach, proposing that broadcasting our location could pose risks, while others believe that the potential for contact could yield profound benefits for humanity. This dichotomy raises compelling questions about the implications of such interactions, not only for our species, but for any intelligent life we may encounter. The moral implications are further complicated by issues of ownership and resource exploitation. As countries and private entities gear up to harvest resources from asteroids or other celestial bodies, concerns arise about who has the right to claim these resources. This dilemma is mirrored by the challenges Earth faces, such as wealth inequality and environmental degradation. The rules we establish for space sharing could echo our terrestrial mistakes, urging us to tread carefully to foster a cooperative spirit rather than a competitive race for resources. Finally, space exploration has profound implications for our understanding of humanity's place in the universe. The decisions we make now about how to approach other worlds and any sentient beings that may inhabit them will shape not just our future interactions in space, but also our ethical framework on Earth. Engaging in this discourse not only prepares us for potential discoveries, but also encourages a reflective examination of our values as a species. The sky may be the limit for the universe we seek to explore, but the ethical ground we stand on must be firmly considered. New propulsion technologies hold the potential to revolutionize human space missions, dramatically altering our capacity to explore the cosmos. Traditional chemical rockets, which have served humanity since the dawn of the space age, are limited by their fuel efficiency and the energy required to escape Earth's gravity. Emerging propulsion systems, on the other hand, offer pathways to reducing travel times and expanding our reach into deeper space. One promising technology is ion propulsion, which uses electric fields to accelerate ions and generate thrust. This method is highly efficient compared to conventional rockets, enabling spacecraft to travel longer distances with less fuel. Missions that once took months or even years could potentially make the same journey in weeks, opening the door to missions to Mars, asteroids, and beyond with a much more streamlined payload. This efficiency could also allow for more frequent missions, thus enhancing our research and exploration capabilities. Another exciting development is nuclear thermal propulsion, which utilizes a nuclear reactor to heat a propellant, significantly increasing the thrust achieved. This could provide human crews a faster journey to destinations like Mars, reducing the time spent in the harsh environment of space and consequently mitigating the impacts of radiation and microgravity on the human body. Additionally, concepts such as solar sails and even theoretical warp drives are being explored. Solar sails harness the momentum of photons from the sun, potentially allowing for prolonged missions without the need for abundant fuel. While warp drives remain in the realm of speculative physics, they ignite the imagination with the prospect of traveling faster than light. Overall, these advancements represent not just incremental improvements, but a transformative leap in our ability to explore the universe, motivating both scientific discovery and human curiosity. As humanity gazes towards the stars, the prospect of crewed missions to Mars stands as one of our most ambitious goals. Current expectations suggest that we could realistically send astronauts to Mars within the next 2 decades. NASA, alongside private companies like SpaceX, is actively developing advanced technologies needed for such a journey. These missions will address multiple challenges, including life support systems, radiation protection, and sustainable practices for long-duration stays on the Martian surface. During these missions, humans will not just visit Mars, they will attempt to establish a foothold there. Initial plans involve sending robotic missions alongside human crews to prepare for their arrival. Establishing habitats, exploring the planet's surface, and conducting experiments will be crucial for understanding the Martian environment and determining the resources available for future missions. This groundwork will play a significant role in enabling astronauts to live and work on Mars for extended periods. But what comes after Mars? The Moon will serve as a stepping stone for deeper space exploration. NASA aims to land astronauts on the lunar surface with its Artemis program, paving the way for sustainable lunar exploration. This approach not only helps refine the technologies needed for long-duration missions, but also provides a platform for planetary science and the staging of future interplanetary missions. Looking even further, destinations like the moons of Jupiter and Saturn tantalize researchers and explorers alike. While these missions may be decades or even centuries away, the newfound interest in exploring such distant worlds may one day become a reality. Overall, the expectations for human missions to Mars and beyond remain optimistic, driven by innovation and an enduring curiosity about the universe and our place within it. Cultural interpretations of space have evolved dramatically over millennia, reflecting changes in human understanding and societal values. Ancient civilizations often saw the cosmos through a mythological lens, viewing celestial bodies as deities or symbols of fate. For example, in Mesopotamia, the movements of the stars were intricately linked to agriculture and governance, with people believing that the heavens influenced earthly affairs. The constellations were not mere patterns in the sky. They were stories that shaped their cultures and social structures. As time progressed, philosophical inquiry and scientific exploration began to alter these interpretations. In the ancient Greek world, thinkers like Ptolemy and Aristotle introduced a more systematic view of the universe, placing the Earth at its center. This geocentric model was widely accepted for centuries, aligning with the prevailing belief that humans were the focal point of existence. However, this perspective shifted dramatically during the Renaissance with the works of Copernicus, Galileo, and Kepler, who challenged the status quo and proposed a heliocentric model, suggesting that the Sun, rather than the Earth, was at the center of our solar system. With the advent of modern science, space took on new meanings, related not only to physical reality but also to philosophical explorations of existence. As technology advanced, our capacity to observe the universe deepened. The invention of the telescope opened up new realms, revealing planets, moons, and distant galaxies, further inspiring a sense of wonder and curiosity. The 20th century brought about the space age, where the launch of satellites and human space travel captured the collective imagination, prompting philosophical debates about our place in the universe and the possibility of life beyond Earth. Today, space continues to inspire awe and inquiry, merging scientific understanding with cultural narratives. From movies and literature to art and religion, our interpretations of space have become more nuanced, exploring not just the physical cosmos, but also the existential questions it raises. As we venture further into the cosmos, from Mars rovers to the search for exoplanets, our cultural interpretations reflect an ongoing journey. They remind us that space is not just a backdrop for human existence, but an essential part of our identity and understanding of the universe. Science fiction and speculation have been instrumental in shaping our understanding of space, allowing both scientists and the public to explore the possibilities that lie beyond our planet. At its core, science fiction serves as a fertile ground for imagination, where ideas about advanced technology, alien life, and distant worlds can be pondered and visualized. Authors like Arthur C. Clarke and Isaac Asimov have not only entertained millions, but also inspired generations of scientists to consider what might be achievable in real-world exploration and technology. These speculative narratives often highlight the scientific principles governing the universe, making complex concepts more accessible. For example, stories about space travel prompt discussions about the laws of physics, time dilation, and even the potential for faster-than-light travel. While many of these ideas remain theoretical, they stimulate conversations and research that push the boundaries of what we think is possible. As such, science fiction acts as a bridge between established scientific concepts and future innovations. Furthermore, the visual imagery presented in science fiction has played a significant role in popularizing space and encouraging public interest in the cosmos. Films such as Interstellar and the Star Wars franchise capture the imagination, helping audiences appreciate the vastness of the universe and the potential for life beyond Earth. This exposure ignites curiosity, leading to greater support for scientific endeavors and increased funding for space exploration projects. In recent years, the intersection of science fiction and reality has become even more pronounced. Initiatives like SpaceX's ambitious plans for Mars colonization have echoes of concepts once thought to be purely fictional. As speculative ideas slowly transition into tangible projects, they not only shape the narrative around space exploration, but also challenge our understanding of our place in the universe. This interplay between fiction and science fosters an ongoing dialogue about the future of humanity in space, highlighting the importance of imagination in the pursuit of knowledge. Ancient astronomical sites provide a fascinating glimpse into humanity's early curiosity about the cosmos. From the Stonehenge in England to the pyramids of Giza in Egypt, these structures reveal that our ancestors were not just passive observers of the night sky. They were keenly aware of celestial cycles, looking up to understand their world and place within it. Archaeological evidence shows that these ancient cultures built alignments with the sun, moon, and stars, demonstrating their sophisticated knowledge of astronomy. For instance, at Chichen Itza, the Mayans designed a pyramid that casts the shadow of a serpent during the equinoxes, symbolizing their reverence for celestial events. This alignment suggests that they marked time and guided agricultural practices based on heavenly patterns, reflecting their deep connection to the universe. These sites served multiple purposes. They were not only observatories, they also functioned as temples and gathering places. The construction of such grand monuments indicates that ancient civilizations integrated astronomy into their daily lives and cultural beliefs. These structures were physical manifestations of humanity's desire to grasp the mysteries of the heavens, and they often carried spiritual significance, linking the cosmic with the terrestrial. As we explore these remarkable remnants of the past, we see that our ancestors were driven by an innate curiosity, a longing to understand the cosmos that continues to this day. Each ancient site is a testament to their innovative spirit and the universal quest for knowledge that bridges time and space, inspiring modern generations to look up and wonder just as they did millennia ago. The overview effect is a profound psychological phenomenon experienced by astronauts when they see the Earth from space. This unique vantage point allows them to view our planet as a small, fragile oasis in the vastness of the cosmos. Floating above the thin blue atmosphere, surrounded by the darkness of space, astronauts often report feeling a deep connection to all of humanity. They see political borders as artificial, realizing that we share one planet, one life-sustaining environment, and one collective future. This experience often leads to a shift in perspective that goes beyond the individual. Many astronauts return with a newfound appreciation for the planet's beauty and the interconnectedness of all living beings. They have described a sense of urgency about environmental stewardship, stressing the importance of protecting our home for future generations. The images and testimonies shared by these space travelers resonate deeply, encouraging a global dialogue about sustainability and the responsibilities of humanity toward our world. As astronauts recount their experiences, the overview effect can inspire societal change. Their stories are shared widely, impacting viewers who may never travel to space. These narratives can motivate individuals and communities to become more eco-conscious and engaged in conservation efforts. The emotional weight of witnessing Earth from above can be a catalyst for building collective efforts to confront issues like climate change and resource depletion, as people are moved by the sense of urgency that accompanies such a powerful visual understanding. Furthermore, as more people come to appreciate the Earth's fragility and beauty, we may see a cultural shift where planetary health becomes a shared priority. The impact of the overview effect extends beyond the space program. It holds potential to unite diverse populations under a common goal of preservation and care for our planet, fostering a new generation of Earth stewards who see the Earth not just as a home, but as a shared responsibility. Art and storytelling serve as powerful conduits of inspiration, igniting public enthusiasm for space exploration in profound ways. Through vibrant imagery, captivating narratives, and emotionally resonant themes, artistic expressions help transport people beyond the constraints of their everyday lives, sparking curiosity about the cosmos. From science fiction novels to visually stunning films, these mediums allow audiences to imagine the possibilities of life beyond Earth, creating a profound sense of wonder. Incorporating the human experience with space, storytelling personalizes the vast mysteries of the universe. Narratives about astronauts embarking on journeys to distant planets or chronicles of fictional interstellar adventures help bridge the gap between complex scientific concepts and the average listener. These stories evoke emotions, fear, bravery, wonder, making the topic relatable and inviting contemplation about our place in the cosmos. Visual art, whether it be paintings, sculptures, or digital creations, also plays a critical role in shaping public perception and enthusiasm. Artists capture the beauty and majesty of celestial phenomena, translating scientific data into stunning visual experiences. Such artwork can evoke awe and inspire individuals to learn more about space science, potentially leading to increased interest in actual space missions and research initiatives. Moreover, public interest is often amplified through events like exhibitions, science fairs, and educational programs that blend art with scientific discovery. By merging creativity with research, they cultivate a community that appreciates the artistry involved in exploring the universe. Ultimately, art and storytelling work in tandem to foster a cultural environment that champions space exploration, making the vast unknown feel accessible and inviting to all. Space has always been a realm of mystery and beauty, and the images captured from it evoke a sense of wonder that goes beyond mere photography. One of the most profound images is the Hubble Space Telescope's stunning view of the pillars of creation. Located in the Eagle Nebula, these towering columns are made up of gas and dust, and their vibrant colors tell a tale of star formation. This breathtaking scene captivates our imagination not only because of its beauty, but also because it represents the birthplaces of stars and the dynamic nature of our universe. Another iconic image is the pale blue dot taken by the Voyager 1 spacecraft from a distance of about 3 billion miles from Earth. In this tiny speck of light, we see our planet in the vastness of space, a poignant reminder of our fragile existence. Carl Sagan, who inspired the image's legacy, emphasized its significance by reflecting on the unity of humanity on that small dot, stirring deep philosophical questions about our place in the cosmos. The cosmic microwave background radiation image offers another compelling perspective. Captured by the Planck satellite, it represents the leftover heat from the Big Bang. The irregular patterns and temperature variations reveal the universe's origins and support the idea of cosmic inflation. For many, this image serves as a connection to the very foundations of existence, sparking curiosity about how the universe has evolved over billions of years. Finally, the stunning photographs of distant galaxies, such as the ultra-deep fields revealed by Hubble, allow us to gaze back in time. Each speck of light in these images often corresponds to an entire galaxy filled with billions of stars. The sheer scale of these photos evokes questions about the universe's vastness and the countless possibilities that lie beyond our own galaxy. These images make the cosmos accessible to us, captivating our minds with the sheer scale and beauty of what lies beyond our world. Eclipses are fascinating celestial events that occur when one astronomical body moves into the shadow of another. A solar eclipse happens when the moon passes between the Earth and the Sun, blocking out the Sun's light, even if just for a brief moment. On the other hand, a lunar eclipse occurs when the Earth positions itself between the Sun and the Moon, causing the Earth's shadow to cast over the Moon. These events, while predictable, are awe-inspiring and remind us of the intricate dance of celestial bodies in our sky. Throughout history, eclipses have captivated humanity. Many ancient cultures saw these occurrences as powerful omens. For instance, in ancient China, a solar eclipse was believed to signify the emperor losing favor with the heavens, often leading to concern and elaborate rituals to appease cosmic forces. The Greeks, too, viewed eclipses as warnings, with notable philosophers like Aristotle tying them to significant natural and political events. Eclipses have also inspired countless myths and legends. For the ancient Maya, eclipses were marked by both fear and reverence. They interpreted these events as significant moments in their cosmic calendar, often seeing the moon as a deity whose temporary dimming could signal a time of change. In many indigenous cultures worldwide, lunar eclipses were viewed as sacred events, deeply intertwined with community rituals and storytelling, which were vital for preserving traditions. In modern times, while we understand the science behind these phenomena, the allure of solar and lunar eclipses remains strong. They continue to hold cultural significance, prompting gatherings for viewing parties and celebrations. The sheer rarity of total solar eclipses, which can be viewed from a limited geographical area, often generates excitement that unites people from different walks of life, offering a moment to collectively marvel at the universe's wonders. Auroras, often described as nature's most beautiful light shows, are predominantly seen near the poles of our planet. They arise from a fascinating interplay of solar wind, Earth's magnetic field, and the atmosphere. The solar wind consists of charged particles emitted by the sun, and when these particles travel through space, they sometimes collide with Earth's magnetic field, particularly at the poles where this field is weakest. As solar wind particles make contact with the Earth's magnetic field, they can become trapped and funneled towards the poles. Once these particles enter the atmosphere, they collide with gases such as oxygen and nitrogen. This interaction results in the release of energy, which creates light. The specific colors seen in auroras depend on the type of gas being excited. For example, oxygen at higher altitudes can produce red or green light, while nitrogen contributes blue or purple hues. The occurrence of auroras is especially common during solar storms, which can significantly increase solar wind activity. These storms often align with the 11-year solar cycle, where periods of heightened solar activity coincide with larger and more vibrant auroral displays. The interaction is most pronounced during the equinoxes in March and September, when the orientation of Earth's magnetic field is particularly conducive to capturing those charged particles. The remarkable displays of light known as auroras are a result of charged particles from the Sun colliding with Earth's atmosphere. The intricate dance of these particles with magnetic forces and atmospheric gases creates a vibrant spectacle that captivates anyone fortunate enough to witness it. The next time you gaze up at the night sky, adorned with these otherworldly lights, remember that you're witnessing a natural phenomenon fueled by our Sun's powerful energy interacting with our planet. Coronal mass ejections, often abbreviated as CMEs, are massive bursts of solar wind and magnetic fields rising above the solar corona or being released into space. When these energetic eruptions reach Earth, they can have profound effects on our planet and its technological systems. These events, primarily originating from sunspots, can significantly disrupt the magnetosphere, the protective magnetic shield surrounding the Earth. One of the most direct results of a CME impacting Earth is the creation of geomagnetic storms. When energized particles collide with the Earth's magnetic field, they can cause it to fluctuate. These fluctuations can induce electric currents in power lines and disrupt electricity grids, potentially leading to power outages. In extreme cases, such as the famous Carrington event of 1859, the impact was so severe that it caused widespread telegraph failures and even sparked auroras visible at lower latitudes than typically seen. Beyond power grids, CMEs can also pose risks to satellites and space missions. The increased radiation exposure can damage satellite electronics, disrupt GPS systems, and even endanger astronauts aboard the International Space Station. Satellites that rely on sensitive instruments may experience glitches or, in severe cases, complete failure, leading to costly replacements and data loss. In addition to these technological impacts, coronal mass ejections enhance the beauty of our skies. The charged particles from the Sun interact with the Earth's atmosphere, creating stunning displays of the auroras, known as the northern and southern lights. These natural light shows are a reminder of the dynamic relationship between the Earth's environment and solar activity, showcasing both the challenges and wonders of our place in the cosmos. Magnetars are a type of neutron star, an incredibly dense remnant left behind after a massive star undergoes a supernova explosion. What sets magnetars apart from other neutron stars is their extraordinary magnetic field, which is among the strongest in the universe. These magnetic fields can reach strengths of around 1,000 million times that of Earth's magnetic field. To put this into perspective, if Earth's magnetic field is a gentle breeze, a magnetar's magnetic field is like a hurricane. The intensity of a magnetar's magnetic field affects its surroundings in remarkable ways. It influences matter in the vicinity, causing phenomena such as starquakes, sudden shifts in the star's crust, which can emit powerful bursts of gamma rays and X-rays. In fact, when a magnetar does experience a starquake, it can release more energy in a fraction of a second than our Sun emits in several thousand years. This immense energy release is what makes magnetars some of the most powerful and intriguing objects in the cosmos. Moreover, the magnetic field is so strong that it can distort the very fabric of spacetime around it. This can lead to unusual effects, such as altering the trajectory of nearby particles and even affecting the flow of light. The intense radiation and magnetic field create a hostile environment that is not only fascinating scientifically, but also terrifying for any matter that comes too close. In recent years, scientists have been studying magnetars to better understand their behavior and the role they play in the universe. Research continues to unveil more about how these massive, enigmatic objects formed and what secrets they hold about the life cycles of stars. As we deepen our exploration into magnetars, we not only expand our knowledge of the cosmos, but also of the fundamental forces that govern it. The history of Earth is marked by a series of cosmic events that have significantly shaped its habitability. These events, ranging from asteroid impacts to solar flares, have influenced not just the planet's surface, but also its atmosphere and biological evolution. One of the most dramatic examples is the impact of a giant asteroid around 66 million years ago, which is widely believed to have contributed to the mass extinction of the dinosaurs and many other species. This event opened ecological niches that allowed mammals to thrive, ultimately leading to the evolution of primates and eventually humans. Besides asteroid impacts, the Sun has also played an essential role in Earth's habitability. Fluctuations in solar activity can have widespread implications for our planet. For instance, solar flares and coronal mass ejections can disrupt satellite communications and even pose risks to power grids on Earth. However, the Sun's consistent energy output has created a relatively stable environment that has nurtured life for billions of years. The delicate balance of radiation received from the Sun allows for moderate temperatures, thus sustaining liquid water, which is critical for life. Another cosmic factor to consider is the influence of supernovae. These explosive events, which mark the death of massive stars, can interrupt the formation of stars and even affect the composition of planetary atmospheres. The remnants of supernovae contribute to the spread of heavy elements essential for life, like carbon and oxygen. When a supernova occurs relatively close to Earth, it could potentially expose the planet's atmosphere to harmful radiation. Thankfully, the nearest known supernova remnants are far enough away that they pose no immediate threat to Earth. Lastly, the gravitational influences of other bodies in the solar system, such as Jupiter, play a critical role. Jupiter's massive size helps shield the inner planets, including Earth, from a barrage of comets and asteroids that could impact our planet. By stabilizing the orbits of objects in the asteroid belt and the Kuiper belt, it reduces the likelihood of catastrophic collisions. Thus, while cosmic events can pose threats to Earth's habitability, they also have laid the groundwork for conditions suitable for life in the universe. Meteoric impacts have played a pivotal role in shaping both the geological and biological history of Earth. These cosmic collisions can alter landscapes dramatically, leading to the creation of craters, the ejection of materials into the atmosphere, and even influencing global climates. For instance, the Chicxulub impact, which occurred around 66 million years ago in what is now Mexico, is famously linked to the mass extinction event that wiped out approximately 75% of Earth's species, including the dinosaurs. This cataclysmic event not only transformed the climate, but also opened ecological niches that allowed mammals to thrive and diversify. Geologically, such impacts contribute to the formation of unique rock types and structures. When a meteoroid strikes the Earth, the intense heat and pressure can melt and vaporize rock, leading to the formation of impactites, which are rocks specifically created by meteorite impacts. Some of these materials can be rich in minerals and other elements, influencing local geology and even providing resources that could be used in various ways by future life forms. Biologically, the effects of these impacts can be both immediate and long-lasting. The debris thrown into the atmosphere can block sunlight, leading to dramatic temperature drops and altering photosynthesis and food chains. In the long run, however, such catastrophic events may also spur evolutionary changes. For example, after the extinction of the dinosaurs, mammals rapidly evolved and diversified, leading to the rise of various species, including ourselves. This illustrates a profound relationship between cosmic events and biological evolution. Meteoric impacts serve as significant catalysts in Earth's geological processes and biological evolution. Their influence is a testament to the interconnectedness of life and the cosmos, reshaping not just the physical landscape, but also the very trajectory of life on our planet. Each impact carries with it a story of survival, adaptation, and ultimately, evolution. The solar system is a vast and mysterious expanse, brimming with unvisited regions that spark curiosity and invite exploration. One of the most intriguing areas lies beyond the orbit of Neptune, the Kuiper Belt. This region is home to countless icy bodies, including the dwarf planet Pluto. Although we have gleaned valuable information from the New Horizons mission, much of the Kuiper Belt remains unexplored. Scientists believe that these distant objects may hold vital clues to the early solar system's formation and the building blocks of planets. Further out, we find the intriguing domain of the Oort cloud, a hypothetical, spherical shell surrounding our solar system. This distant region is thought to be the source of long-period comets. However, because it is so far away, potentially at distances of over 100,000 astronomical units, no spacecraft have ventured there. Exploring this region could unlock secrets about the solar system's outer limits and even provide insights into how other star systems might form. In addition to the icy realms, there are opportunities to explore some of the lesser-known moons of our solar system. For instance, Europa, one of Jupiter's many moons, is covered with a thick ice shell that may hide a vast ocean beneath. The potential for life in such a hidden environment presents an enormous draw for astrobiologists. Scientists are eager to send missions dedicated to drilling through the ice and analyzing the subsurface ocean for signs of life or prebiotic conditions. Finally, we shouldn't overlook the significance of asteroids within the belt situated between Mars and Jupiter. While missions like the Hayabusa and OSIRIS-REx have successfully returned samples from these celestial bodies, many asteroids remain unexplored. Studying these asteroids could yield insights into the organic molecules and water that were essential for life on Earth. Furthermore, asteroid mining could one day provide resources for future human endeavors in space. Thus, each unvisited corner of our solar system is not just a geographical mystery, but a tantalizing opportunity for discovery and knowledge. The prioritization of missions to distant or unknown celestial bodies is a complex process driven by scientific goals, potential discoveries, and the resources available for such explorations. When scientists propose missions, they begin by identifying the objectives they wish to achieve. These could range from studying the geology of a planet, understanding its atmosphere, searching for signs of life, or even understanding the origins of the solar system itself. The potential for making groundbreaking discoveries is always a significant factor that influences mission selection. Another crucial element in evaluating potential targets is the feasibility of the mission. This involves considering the technology available, the time required for travel, and the costs associated with the mission. For instance, a probe sent to the outer planets like Uranus or Neptune faces not only long travel times, but also immense challenges in communication and energy supply. Missions to destinations that are easier to reach, like asteroids or nearby moons, often gain favor simply because they promise a higher likelihood of success within established budgets and timelines. Scientific collaboration also plays a vital role in mission prioritization. Agencies such as NASA and the European Space Agency often rely on input from the broader scientific community. Research proposals are routinely submitted and peer-reviewed, ensuring that various opinions and insights shape the final decision. Furthermore, missions that can leverage international cooperation may have an edge, sharing the financial burden and pooling expertise to enhance the chance of success. Finally, public interest can't be overlooked. Missions that capture the imagination of the public tend to gain more support and funding. Space missions that promise exploration of thrilling targets like Mars or intriguing moons such as Europa, which may harbor subsurface oceans, draw attention and support that can influence decisions at the highest levels. The prioritization of space missions intertwines scientific merit, practical constraints, international collaboration, and public fascination, creating a robust framework that guides our exploration of the universe. The Oort cloud is a fascinating region that lies at the fringes of our solar system, and it represents one of the final frontiers in our understanding of this cosmic neighborhood. Thought to be a vast, spherical shell of icy objects, the Oort cloud is located far beyond the orbit of Neptune and extends nearly 1 light-year from the Sun. This distance suggests that it could contain billions of comets, each composed of ice and rock, remnants from the early solar system. Yet, despite its importance in understanding our cosmic history, the Oort cloud remains largely shrouded in mystery. The significance of the Oort cloud goes beyond its mere existence. It acts as a reservoir for comets, which occasionally make their way into the inner solar system. When these comets approach the Sun, they can develop bright tails and become visible from Earth. Studying these celestial visitors provides scientists with valuable insights into the conditions of the early solar system and the formation of planets. Since the Oort cloud is thought to contain materials that have remained largely untouched since our solar system's formation, each comet may carry secrets about the elements that were present billions of years ago. Moreover, the Oort cloud has implications for understanding the dynamics of gravitational influences within the solar system. While we cannot observe the Oort cloud directly, its presence is inferred from the orbits of long-period comets. These comets are believed to originate from this distant region, suggesting that some external force has nudged them into paths that bring them closer to the Sun. Such forces could include passing stars or even the gravity of the Milky Way itself, indicating that our solar system is not an isolated entity, but is engaged with the broader cosmic environment. Lastly, the study of the Oort cloud undoubtedly raises even more questions as researchers continue to explore its characteristics. How did this cloud form? What determines the orbits of these icy bodies? Understanding the Oort cloud offers not only a tantalizing glimpse into the past, but also insight into the gravitational ballet that influences the dynamics of celestial objects. As investigations continue, the mysteries of the Oort cloud enrich our picture of the solar system and illuminate the pathways of our cosmic journey. Phase space mapping is an innovative approach that can deepen our understanding of the cosmos by visualizing the states and dynamics of various celestial bodies. Imagine a multidimensional representation where every point reflects the position and momentum of an object in space. This technique allows us to track not just where things are, but how they move and interact over time, revealing complex gravitational relationships that are not easily captured by traditional mapping methods. As we apply phase space mapping to our cosmic cartography, we gain insights into the dynamics of entire systems. For example, instead of simply knowing where stars are located, we can observe their trajectories through the galaxies. This adds layers of data that reveal how gravitational forces influence galaxies, star clusters, and even dark matter. It provides a more holistic view of cosmic structures, offering a deeper understanding of the universe's behavior and evolution. Furthermore, phase space mapping can help researchers identify patterns and anomalies in cosmic phenomena. By analyzing how celestial bodies interact within this multidimensional framework, astronomers can uncover the underpinnings of events like galaxy collisions, star formation, and the behavior of exotic objects like black holes. Such information can lead to breakthroughs in our understanding of the fundamental laws of physics that govern the universe. This powerful tool not only enhances our current models, but may also lead to unexpected discoveries, allowing us to ask new questions about the universe. As we refine our techniques and technologies for phase space mapping, we may uncover new components of the cosmos, providing a richer, more intricate picture of the universe we inhabit. It's a fascinating leap forward in the quest to explore the expansive, ever-evolving cosmos. Interstellar travel, the journey between stars, promises to be a realm filled with surprises and wonder for future explorers. While the technical challenges of traveling beyond our solar system are immense, the potential discoveries awaiting brave adventurers could redefine our understanding of the universe. Imagine encountering worlds that are not only vastly different from Earth, but also host phenomena that challenge our existing scientific theories.